And the chill is starting in here tonight, I can tell you that. Well, hello and welcome to this October 27th and 28th, 2017 SkyTour LiveStream, coming to you live from the John Zach Memorial Observatory in northwestern Connecticut. Now, tonight it's an exceptional night and we're going to see some wonderful glittering jewel boxes of stars, but we're also going to take a look at our closest neighbor, the moon, and we're going to explore some planets in all their glory. So from wonderful star clusters to wonderful planets, we're going to see them all, because tonight it's Moonlight Potpourri night. And as you know, we'll take questions from the chat room, thanks to Amanda, who's going to be looking at the chat and hanging out with you guys. And we'll see you in a short moment. And that short moment is up. Here I am. Hey Amanda, how are you?
I am well. How are you?
I'm very good, thank you. It's a chilly night.
Posting links.
Huh?
Sorry, I was on mute. I was posting links. Hello, everybody in chat. Hope you're having a nice weekend.
I'm sure they are. They're wonderful. We're having a good time. No, tonight is Moonlight Potpourri night. And what does that mean? It means that we're going to go anywhere our little old heart desires, because when the moon is out, you might think, well, our choices are somewhat limited. That may be true, but take a look at what we're seeing on the screen right now. We're actually seeing a star that's very near the moon, and this star is actually near this first quarter moon. I'll show it to you in a bit. I'm overexposing the moon so we can see that star, but the star itself is called Okul, and it is Okul to see it, and it's actually in our Greek alphabet for the brightnesses of stars within constellations. It's Pi Capricorni. Now, the star itself is actually a triple stellar system. It's a triple star system in the constellation of Capricornus, and it's around 670 light years from the Earth. And right to its lower left is the moon, which is 240,000 miles from the Earth. But with no sense of distance or scale and this imagery here that we see, there's no way to realize that that star is so much further distant than our moon. But I will say this, it is really cool to see what are called occultations. Now, earlier during the day, the moon actually passed in front of Okul, but we couldn't see it because the star is so much dimmer than the bright blue sky, so it was hard to tell. I didn't see it. Nobody really got to see it, of course. So the interesting thing is, that is, no one in the United States. The interesting thing is that as the star emerged from the limb, we could have actually done some interesting views of the star emerging, and you would have seen the star blink a little bit. It would dim and it would blink. It would look like it's dimming and brightening, and that's actually the starlight, which is always a point of light, a really, really tiny point of light. Remember, because stars are so distant. We would have seen that star, actually that light dancing for just a fraction of a second as it emerged from the limb of the moon. And that's because we would be looking at the mountains of the moon, causing the starlight to be blocked and then allowed to be visible again. That's a very cool process. It's neat. And you really see that our moon is actually, has some height to it, has some mountains and valleys. You can actually see that when you watch a stellar occultation like this. But this is Okul. That's O-K-U-L. And Okul is very neat, but Now, it's not the only thing we're going to look at tonight. We got a few planets to look at. We got the moon itself, and then we're going to look at some star clusters as well, and just have general fun. Now, any of you guys in the chat, if you want to see something, just let us know, and I'm sure I'll get the message. And Amanda will pass it on to me because she's been very, very good at doing all these things and helping out and making it actually work. So I want to thank you, Amanda, for that, because you do make it work.
I do my best, but I mean, it's really just keeping an eye on chat because, like, you know, the people in there are so awesome and so smart, and they always have great questions or great requests. Actually, speaking of chat, I was just watching what was being said. First off, could you spell this star's name again, please?
Yeah, it's spelled O-K-U-L.
O-K-U-L.
Yep.
Okay, because actually, I guess a few people were talking about this very star last night. I've never heard of it before, and I said, well, what specifically were you guys wondering or talking about? And they said that they were trying to find this on the sky map, but couldn't figure out which one it was. So, I don't know. How can people find it, like, without specific coordinations? Is there a way to kind of... Yeah,
there is.
Thank you.
Yeah, there is. One way you can really look this up right away, and very easily, is as long as you remember one phrase: Google is your friend. If you type in stars near the moon tonight, or oh cool by that name, if you knew the name, then you would get the positional information. You get all the information about oh cool. It would tell you that it's close to the moon. It would give you all that information. Also, if you download the free program, and I did say free, those 4 wonderful letters, the free program Stellarium, which most of you know, okay, that's Stellar Eum, I-U-M, Stellarium, you can actually get an image of the night sky that's very, very close to reality, and you don't even need SkyTour LiveStream anymore, for crying out loud. You can actually just go look. Well, actually, you want to come to SkyTour because, you know, we're doing things that you can't get in Stellarium. But what's interesting is, I want to just show you this. We, earlier in the night, just a little while ago, okay, notice the distance between Okul on the right and the moon's limb, all right? I want you to notice that. And when we come back and look at it later, you're going to see that the distance has become greater. You can actually measure the distance. You can actually then tell how far the moon moved in a certain amount of time. And based on its mass, you know how far away it is in its orbit, and you can calculate how fast it's going through space in this way. Now, we're not going to do that, but I'm just telling you this is something that we can do. It's very, very interesting. It's a neat little project. Now, just to show you what I'm talking about, let me just pop out of this high magnification for a sec. There you see. All right. Now, clearly, if I come down to the point where the moon is actually, you know, looks halfway decent, then clearly we can't see Okul. I don't think we can, actually. Let me just zoom in and see if it's even faintly visible.
I thought I saw it faintly before you started darkening it. Oh, I'm watching on YouTube. I forgot. He's actually
yeah,
I'm so used to watching on YouTube. He's actually screen sharing with me so I can watch it live. Let me pop out the chat here.
And the only reason I do that, folks, is just because you're hearing it and seeing it, you know, in real time for you. You're hearing my voice 30 seconds delayed. You're hearing all that. But if someone's on Skype with me, like Amanda usually is, then her voice is also 30-second delayed, but she's seeing the imagery 30 seconds later as well. So if I say, oh, look at that, Amanda, she has to wait 30 seconds to see it. So I'm screen sharing my screen with her now that I've got internet that's literally 10 times faster than it used to be. And then she can actually see in real time, because we're both delivering SkyTour LiveStream to you, so it's important that someone who's working with me on this see the sky as I see it. So that's what that's about, and that's what we're seeing right now. So
actually, now that I'm looking, can you try to lower my audio, please? The one with the little speaker, because people are still saying I'm way louder than you.
Let's do this little experiment.
Yes.
Okay, so I just I just
Okay,
dropped.
guys, how do I sound now? We'll give him 30 seconds.
Okay.
Did this make a difference?
Did I lower her successfully, or did I lower all of us? That's the question. That's what I'd like to know.
I think the mic is you and the speaker is me, but that's just a guess.
Okay, but I think the mic.
But yeah,
I thought the speaker was output for the stream, but maybe it's not. I'm always willing to try this.
Okay, well, we'll give him a minute.
We're waiting a minute. It's still your turn. Okay.
Okay. Let me just see here. I think.
Look at that. It's so beautiful.
Laura wants to know if the Chinese are on the moon yet. They are, aren't they?
Yes, they are.
Were they not one of the first after the States? States and Russia and China? Were they not kind of the top three, or?
Well,
I could be way off.
Yeah, you're kind of off, but that's okay. I mean, it's an easy mistake to make because, you know, the Chinese aren't very forthcoming on what they do. The truth is, the Chinese landed on the moon. I think it was last year, didn't it? They put a lander, a little rover on the moon, and it rolled around. And then, of course, the Lunar Reconnaissance Orbiter actually saw it and caught it from space, which is really cool. You know, it was traveling 30 miles over the site, so they could look down and actually see it, you know. This is a very still night. Look at that. The moon isn't even dancing around with its typical, you know, crap that you always see, the typical waves or the heat. So I'm very impressed. Very nice night. So let's go to the Terminator. Oh, look at that.
They're saying it's about 40% you, 60% me for the volume.
Still?
Yeah.
All right. Well, I'm gonna drop.
Did you guys notice a difference? I mean, some people are saying it's fine. Some people that are regulars here and always experience this.
Yeah.
They're the ones that are saying it's still kind of.
All right. Well, I'm gonna drop you.
And I think Jello just turned on his put on his headset, so that'll make a difference.
All right. I just dropped you 2 more bars. And hopefully I didn't drop.
I'm very loud anyway.
Hopefully I didn't drop myself 2 bars, but we'll see. Wow, look at this. This is pretty. That's really, really beautiful right there.
It looks so close. I just can't get over it.
Yeah, well, what I like.
And that's why when you see it that close, I can understand why people don't say, well, can you zoom in a little more and see the flag? Because, I mean, that looks like... that, you know, it doesn't look like miles away. It looks like almost like when you're taking off in an airplane. Yeah. You can still make out the ground and the features before it's all just little dots, and then you can't make it out, you know? So
That's true.
I get why people ask that, because it does look so close. So detailed, so clear.
And look at that modeling in that dark soil there. I mean, that obviously that's like, you know, a couple 100 miles worth of dark black soil that you're seeing there in the view. But that's really impressive. You know, it's a beautifully still night. I mean, this is really pretty. I don't usually like to look at the moon because it ruins my night vision, but look at this. Look at the delineation here between that Maria above, the one that's up here, okay, and the one down here. Look at that. And you can actually see separate coloration between that crater that's right there on the right. Now I am using a filter, okay, to help enhance this, by the way. So that's one little thing I didn't say, but that's pretty cool because the filter really shows some neat differences here. It does make it look bluer than it is, though. So what's the verdict on your volume, by the way? I want to get that straightened out. If we have it figured out, that's great.
Jello says if you do it just a touch more.
Really?
Yeah. Cuppy is still saying that she hears me in an echo, but
Christ.
I don't know what that could be.
We're gonna fix that.
I wouldn't be surprised if you took the music out.
And it went away?
Because I don't know. I think on Skype, since my audio and the music audio is both on the same track, I think it's like we're fighting over what volume Skype is picking up. or possibly OBS, but that's just my guess, and I don't know what I'm talking about. So.
No, it's okay. I mean,
the volume I'm pretty sure is what we're doing now. The echo, I don't know.
Okay, well that's fair. I mean, I'd like to see, and we'll get this all straightened out, and I'm looking forward to hearing what people say.
As long as I can hear you clearly, because you're the man with the information.
No,
so
but still, you know what I don't like? I don't like the fact that, you know, you're asking questions and you boom into people's ears and they shy away. And what that does, okay, is that says to people, I'm done with this garbage. You know, they can't get their act together. I totally understand that. So it's time for us to get.
Who said that?
I'm just guessing that people would get tired of trying to, worry about listening intently to me because I'm not so loud, and then you come in with a question and you're like really loud. It's not your fault. It's not your fault. It's how my setup is, and we're working on it. I'm going to get another mixer board in the observatory that's going to take that problem totally away. And it's not here yet, but when it comes, this is going away, and I will no longer have the issue where I have to worry about your volume, or you have to worry about your volume. I can make you louder.
They're saying my volume's all right now.
Okay.
Just the echo, which I can't do anything about. I mean, if you turned up the one on the microphone, that might raise your volume a little.
Okay, well, we can, but does mine have to go up?
Well,
I mean, I just went up another notch. I don't know if mine has to go up actually, but I do want us to be equal in volume. I don't want us to, I don't need to boom over you. I mean, because we're sharing information with the stream participants, all of our friends out there, and so we do it equally. I don't have the need to be Mr. Big Control, Big Shot. I don't have that need.
Hold on. The music is coming in from your cell phone, though, right?
Well, it's a line in to the mixer board. It's a separate line in, and I have a separate volume for that entirely. So, and that's on my phone. I'm using the music setup on my phone. Like, it's louder here, and then softer. See, so I can make it louder and softer without affecting your volume at all, because I'm using my phone. Effectively, it's a mixer.
Yeah, no, sorry, I'm just reading the comments.
No, it's fine.
Because actually, Jello's trying to help us out here. He was saying, Mark's capturing the desktop audio for the music. That's why I said it's not. It's your phone, right? So I wanted to come up with maybe another suggestion.
Yeah, it's not desktop audio.
I am wearing headphones, so that's not where the echo's coming from either.
Yeah,
Mark doesn't have a secondary camera on that's picking it up. Both of our YouTubes are on mute, so it's not that picking it up.
And you notice I turned that off. I turned that camera off just to test. Yeah. It's been off for a little while over there. All right. I'm really having a good time looking at the screen. This is beautiful. This is gorgeous. I've actually, I'll be honest with you guys, I've never actually seen the moon with this much clarity as we're seeing it tonight. I'm just amazed at how clear we're seeing it. It's really quite pretty. Look at these mountains.
It almost looks like half a smiley face.
I know, right? And in the center of the screen there, you see a crater that's fairly faintly outlined because it has just come a little bit down lower. Let me just bring it down a little bit. Hang on. Okay, it's on. There we go. So it's coming up slowly into the center of the screen. There it is. Okay, right in the center. You see that round crater? It has another one inside of it. Mm-hmm. That's a lunar bullseye right there, because that crater that's on top of it came much later. How do we know? Well, because that first crater would have excavated a huge amount of lunar surface, and any small craters that might have already been there would have been wiped out by that impact. So that's how we see the chronology. I know it's a little thing, and I know most people probably know that, But when you actually think about it, if you don't know that, then you go, oh, I get it now, you know, and that's kind of what we're looking at here. So very interesting, you know, and I think that it's very you know, telling of how things in the moon work.
Vicky is wondering if you could go back to the Terminator and run up it.
Sure. Let's do that. Let me bring my speed up just a tad. Alright, let's get this hot rod going. Let me just do something here. Set my speed to something a little bit slower. Let's go to that. No, let's go to this. Okay, hold on. Speed. There we go. Let's try this. Alright, so let's go up. Go, there's the pole, there's the north pole of the moon. Now let's go down. Drop down a little bit. Wow. And over there, just below center and right, is that crater that I said is a lunar bullseye.
Mm-hmm.
And then we go down a little more. It's really interesting to see the partially illuminated craters, like the one right there in the Terminator. You can actually see the rim illuminated because it actually stands up off the lunar surface enough that the sunlight can come over the top, as you see there. Now, you say, well, it's interesting, it's brighter than the other side. Why is it brighter than the other side? And that actually isn't such an easy question to answer. And the answer comes from the fact that we're seeing mostly the material that's inside the rim of the crater. And on the right-hand side, we're seeing the material on the outside. The material on the outside tends to be rough and jumbly, and it tends to disperse the light. But the material on the inside of the crater, all right, like you see on the left edge of that crater, that material is actually a very that stuff is very, very smooth because it's had time to weather down. And so in a crater that doesn't have many terraces, like Copernicus has terraces, you'll see this type of effect. You'll see the left-hand side, that is the side that's just being illuminated, being much brighter than the right-hand side. And again, when it's smooth, then a lot more of the light can be reflected directly back toward the Earth. And that's what we see here. So I think that's actually pretty cool to see this way, and it kind of gives you an idea about you know, the physics of light too, because we see how the light is reflecting, and it has to do with what's called the reflectivity or the albedo. That word is A-L-B-E-D-O, albedo, or reflectivity of the stuff that's in the crater. And in this case, we see that very, very clearly. If you look at the lunar mountains down here, okay, you'll see that some parts of the mountain that are to the right of the shadow and a little bit lower to the right, you see that it has a bright reflectivity as well. That's because there are sections of that mountain that are actually very reflective because of the nature of the terrain right there. And we see that. Now, my favorite craters are the ones where they get illuminated just enough so that you can see the central peak illuminated as well. Now, these craters here, down below, okay, if we keep going down more, alright, let me go over here a little more, okay, there's another crater that's really well illuminated, that little tiny one in the middle, but just now down to the right here, I'll just go down a little more and then come over. This crater right here that you see in the center, this guy has a little central peak, and you can actually see the shadow of that central peak. It looks very nice. You can see it's a little tiny central peak. Now, these are complex craters, and when people say, well, you know, these are flat on the bottom, actually, the bottoms of the craters aren't really fully flat. They're kind of wavy in a sense, but you don't see that because you're so far away from the moon at this point. It tends to look just all kind of plain, bland gray. But if you do what I said to do before, which is go to the Lunar Reconnaissance Orbiter Quick Map site and check out the moon, you can zoom in and see the terrain, and there's in the upper right of that screen, you have a tool with which you can actually sample a linear stretch of the moon. You draw a line, and then it draws a profile curve. And you'll be amazed to see how sometimes what you thought was terrain that was just flat actually rises up by 1,000 feet or dives down by 500 feet or more. It's really incredible to see this, and that actually helps us out quite tremendously when we're trying to do the stuff we do with our 3D craters. All right. Now right here we have two craters like I was talking about. See the central peaks of these two in the center? You see the very tippity tops are illuminated, and they really kind of look cool, you know, and the far rims are illuminated, but you can see how the sun's coming over. Those are classic complex craters. They actually have a high enough central peak that it's illuminated fully, even in this dim light where the light hasn't reached the crater floor yet. On the lower crater, it's closer to the crater floor than on the upper crater, you know, and that just has to do with, you know, how high the crater walls are and how high the terrain is next to the impact site. Sometimes when a meteor hits, it puts up a huge wall of ejected material that rings the crater, and so it becomes kind of difficult for material to actually be visible during the sun's passage across. You just don't always get to see that. But I think this is move the dome a little. Okay, here we go. There's the moon. So this is really interesting, and that's what I was talking about with the complex craters before, with the central peaks. Now let's just go down a little more here and survey the Terminator. Now I want to show you.
And so, well, what is the Terminator, and how did it get its name?
The Terminator is where the light terminates, basically. It's the division between, it's basically where the shadow ends. It's like when you hold your hand up in the sunlight, and you look on the side of your hand, you see the front of your hand is illuminated by the sun, the back of your hand is dark. But in that middle spot, where the light meets the dark, okay, that's the Terminator on your hand, so to speak. All right? That's the
Does it move throughout the 28 days, or is it only like when it's directly split in half?
No, the Terminator is the term for the transition zone between the lit side of the moon and the dark side of the moon, wherever it may be. So even when the moon's full, there's a Terminator, and you say, well, how can that be? It's because the moon is a ball. You just can't see the Terminator.
The other side, yeah.
There you go. Well, it's on the edge, right? It's on the edge of the moon as seen from the Earth, all the way around. So you can't see that, you know, because, of course, and then most of the material, most of the light is being reflected from the craters back to your eye, and you don't have the benefit of shadows during a full moon. So the only place that we have shadows at a full moon is actually on the lunar north and south poles, because there's places on the poles where there's sunlight never gets to. In other words, can you imagine that? Craters on the moon that are always dark, and there's no atmosphere. So what that means is that we would see that the area that we're looking in, if we had a moon base there, would always need lights. We could never expect sunlight to come in at some point during the month and illuminate. We could also never expect any heating either from the sun. And of course, as soon as you step into the lunar night, the temperature drops several hundred degrees. And you say, well, wait, how can that be? On the Earth, you can't go like 20 feet and get a 200 degree drop in temperature. And that's true. That's because we have an atmosphere. An atmosphere does a very good job of mixing thermal energy. So we actually see warm areas that are never illuminated on the Earth, because the ground is warmed and then it radiates heat into the dark areas. This also happens on the moon too, you know. If you looked at it right now, right in this image, an infrared view of these lower cluster of craters that you see, that really beautiful cluster, you would see that the dark areas are also a touch illuminated by infrared energy. And the reason is because the lunar soil is absorbing this radiation, and then it re-radiates it. Okay, and there's no, and this is hard to explain a little bit, I think, but there's no definition of temperature when you're in space. And you'll say, well, wait a minute. I mean, people say it's always minus 400 degrees or whatever, you know, in a shadow on the moon, and, you know, plus 200 or 400 in the sun or whatever. You know, they make up numbers. Well, the thing is, that's putting it in a context that they can understand. But the fact is, all you have in space is absorption and emission of radiation. What does that mean? It means that a particle of ice floating around the space shuttle isn't instantly vaporized by the sun. In fact, it stays for hours, sometimes days, and floats around the shuttle, like Pigpen and Charlie Brown. When the shuttle was going up, the shuttle always carried with it a debris cloud from the Earth, which included a lot of ice. And when this debris cloud shed, as the ice began to sublimate, because that's all it does in space, it doesn't, it doesn't melt in the traditional way. It doesn't turn to water. It goes right from solid to gas. That's sublimation, and that gas, of course, is this, H2O molecules. Well, when it does that, we actually see, the ice particles separate from each other, say on an instrument inside the shuttle bay or whatever, and then they eventually will fall off. Okay, and when they do, they just float there. There's nothing to disturb them. And sometimes they have some trapped air in them, and when the ice particles sublimate a little bit more, the trapped air bubble gets out, psst, and the thing shoots off in a strange direction. This has given rise to many videos that say, look, NASA's hiding aliens at the space shuttle location, because they show this thing moving at an apparent 90-degree angle. And when you learn more about how the shuttle operates and how ice works in space, then you can see that not everything is not everything is a UFO. Unfortunately, I wish it was. I'm a grand believer in it, as you all know, but I do believe that if we can explain it in a rather mundane way, easily, then that's probably more than likely the explanation. So, when we saw particles of ice come off the shuttle and dance around the other way, the other thing that can happen is that the RCS system on the shuttle might have fired. Now that's the reaction control system, and those little nozzles that you see in the nose of the shuttle that were there and elsewhere, and all space vehicles now have reaction control systems, but they're no longer called retro rockets. They're not firing jet fuel or rocket fuel to create thrust. They're actually expelling gas. It's clear. It's not hot gas. It's actually just gas being expelled to actually make microscopic adjustments to the attitude of the spacecraft. The Soyuz spacecraft, the Russian spacecraft, and so forth. So when we look at them at the shuttle, it was the same thing. They were using the RCS with these little tiny bursts of gas inside the shuttle. You actually heard them fire, and it sounded like this. They would fire the reaction control jets, and you hear, and that's how they actually sounded. They were like a quick, and you'd hear it from inside. It sounded like a bang, but that's just a little reaction control jets firing, sometimes autonomously to hold stable position while docking with the space station. But I could imagine if you didn't know better, you'd think, "What's that? What's that? Is the shuttle breaking apart? Oh no!" But that was just normal. Now, when those jets fired, they also impacted ice particles sitting right outside the nozzle. And many times, there's videos, which I've seen on a lot of TV shows where I had to, analyze them. They show these particles shooting off in another direction, going 90 degrees away. Bam! Wow, look at those 4 particles zipping off at high speed. Those are UFOs. Well, only until we identify if it's water ice or, ice from, something else, it could be ice from, space or whatever. But that's the only reason it's unidentified. Otherwise, it's very much so a mundane object, I hate to say. And I'm sad that whole genre of UFOs got loose on us, because that's a genie you can't put back in the bottle. Once people start thinking they're seeing UFOs in the shuttle missions and the ISS missions, you're not gonna get past it. No one's ever gonna believe you when you tell them the other things, and that's too bad. That's too bad. Wow, I'm just, like I said, I'm really liking this view. I mean, this is really ultra stable. I'm going to just touch the, I'm going to change the magnification here for a second. See, I'm just a touch hot on the magnification. Let's just bring it down a little bit and jump back in. Wow. That's something else. It almost looks like a photo. It's dancing a little bit, though. Boy. This reminds me, I don't know if you saw my Facebook post, but I did a 3D print of Occator crater, which is on Ceres. And that crater was one that had these two bright spots in it that people looked at and said, whoa, what are those two bright spots? Is that an alien construction or something, an alien domes reflecting light?
Why does that always have to be everyone's first guess?
Because we are desperate to make sure and find out that we're not alone. We're
yeah, but I mean, if it was like
people.
ice from water, I mean, then you could say, okay, if we can prove it's water, then things could grow. Well, like, why does it have to be made by aliens? Why can't it just be inhabitable for them, you know?
Yeah, and Amanda's right, guys. I mean, it actually is. It's actually water-based salts that it turns out these things are. These bright protrusions on from Occator crater. And if you look at that Facebook post, I actually printed it in 3D, and it's one of the craters we're making available, you know, as part of SkyTour LiveStream if people want it. But you can get any crater you want. That's you know, just so you know. I mean, any crater you're looking at right here on the screen, if you like it, it's your favorite crater. You know, if you like these craters like frozen peas, if you have a favorite frozen pea, we can print it out for you. So that's a George Carlin joke. You know, if you had a favorite frozen pea and you drop it on the floor, it's gone. You'll never see your favorite frozen pea again. Very cool. So I'm really fascinated with this entire with this view. This is just stunning. What do you think, Amanda? Is that pretty or what?
It is very pretty.
I'm just finding that to be just beautiful. Just a beautiful.
I can't believe how crisp it is. It's just like,
yeah.
You can almost feel how rough and bumpy and the grooves and
yes.
Like it's hard to believe. Like, I imagine if I walked outside right now and walked into my backyard and I looked up at the moon. I mean, that's basically what you're doing. Like, from your front yard, you're getting images this close. Like, this looks like a rocket ship is about to land on the moon, and we're seeing the descent. Like, that's what it looks like. It's that close. It looks like we're coming in from a descent. Or, you know, satellites, like, hovering by really, really close or something. Like, it's just hard to believe you can, like, take a few steps out of your house and have this kind of detail just at your fingertips, so...
You can do it too if you don't mind freezing. I'm kidding on there. Obviously, I'm handling it. I'm hanging on. I'm okay.
In my nice cozy basement.
Yes, I hear you. It's okay.
I get pity shivers though. When you say burr and you can't feel your feet, I get a little sympathy shiver, but...
Well, thank you, I think.
Then I just turn my heat on and forget about it. I'm just joking.
No, it's okay. I mean, I don't want anyone to be cold. I want them to be able to, stay warm.
Well, and Genghis said it was raining where they were. It's pouring. I think that's what gave me such a bad headache the last 2 days. It's just pouring, and during the Orionids, it was just rainy and cloudy and ridiculous. So we're just so lucky to have people like you actually streaming this for us when you can, because a lot of people want to see this and they can't. They can't, even if they have telescopes. If they don't have the weather, if they don't have the clear skies, or if they don't know exactly what they're looking at. Like, you can get great images, but, you know, you can only be so impressed with if you don't know what you're looking at. Like,
Yeah, perhaps, but I get your point.
like, I mean, to me, any group of stars I see in the sky may as well be a star cluster. You know what I mean? Like,
Yeah, I mean,
because I don't know.
Actually, though, think about it. What you just said is actually kind of important, actually. You said something that's very good, and that is, and a good observation, any group of stars I see in the sky could be a star cluster. And you know something? That's true. For example, when you look toward the eastern horizon right now, we've got the Hyades coming up with red Aldebaran, which is the eye of the bull in Taurus. Well, the Hyades are a star cluster. Aldebaran's not part of that star cluster, by the way. It's actually it's a star that's just in the same field of view. But the Hyades star cluster are fairly young stars that are actually in this cluster, nice and visible. And if you look at in the constellation of Perseus, the star Mirfak, M-I-R-F-A-K, Mirfak. Okay, Mirfak is actually part of a star cluster within Perseus. All right, and so it just happens to be relatively close by, and so we don't recognize it as a star cluster. But think about this: if there's somebody that's, say, 1,000 light years away, looking back on the Ursa Major, what we call Ursa Major, well, they wouldn't see the stars, of course, in the same orientation and same layout, of course, because it's a 3D universe, so they would see them their way, whatever that is. But if they looked at the Big Dipper, the asterism stars that are the Big Dipper, remember an asterism is a pattern that looks like a familiar object within a whole constellation, say. The Pleiades, for instance, is a asterism within Taurus. If they look at the Big Dipper stars, then they're probably going to look like a small cluster, and that's because they are. Right? Most of them, not all of them, but most of them are part of the same cluster that they were born in. And there's some thoughts that say that the sun was one of those stars as well. That's why the Dipper stars are so bright to us, because we migrated away from that position. But there's no way for us to know. There's no way for us to know. We can't see where we've been. We can only see where we're going. That's how we know, for instance, that the Andromeda galaxy, 2 million light years away, is going to be colliding with our whole Milky Way galaxy at some point. Now, collisions like that are nothing to worry about. I mean, if this was imminent, tomorrow, it would be one of these things when it starts to happen, it'll be quote unquote imminent for like tens of thousands of years, okay, or even millions of years, because it'll take that long for the galaxies to actually, merge and do the thing that galaxies do when they collide, which is to blend their spiral arms together, start off all kinds of new star formation, perhaps starburst formation, like in the famous M82 galaxy, what used to be called the Exploding Galaxy, and that's in Ursa Major, which is the Great Bear, and we'll see that again, and or not. So it can, this starburst formation is something that may occur when galaxies come together. The other thing that might happen when galaxies come together is that we might have a new form of galaxy. That is to say, a galaxy we've seen before, but perhaps a galaxy that is, new for us, and that would be something called an elliptical galaxy. It's possible that these galaxies, elliptical galaxies, which are like the attendant galaxies around the Andromeda galaxy, they're called companion galaxies. When spiral galaxies combine and collide, it's possible that they are actually creating a brand new elliptical galaxy. Now here's something right in the center of the screen. I'm going to test the chat and see how many of you know what that crater is with those very peculiar rays that you see emanating to its left. There is a crater that is in the center of the screen that's associated with those rays, and then right to the right hand side there's another one, and those craters are the same crater name, has the same crater name but a different letter associated with them. Those are called satellite craters, and not because satellites made them, but because the main crater and other craters around it that may or may not have formed when it formed, because of its association, because of the landforms, and because of the the whole topography was altered by these craters that happen near each other over long stretches of time. Sometimes they name these smaller craters satellite craters. So, does anyone know what that crater right in the center is? It has those strange rays. Do you see those rays? Amanda, do you see those rays?
I'm not sure if I see any rays.
Okay.
I see the two craters.
Well, I'm talking about right in the center of the picture. Okay.
Okay.
Right in the middle of the dark Maria there.
Mm-hmm.
You'll see something that looks like a streak going to the left.
Okay, yeah.
Okay, that's actually two basic rays. All right, if you look at it carefully, you see there's some dark between it. Okay, and I'm asking the chat if you know what that crater is. I know the answer. I'm trying to. It's a little quiz.
Okay, well, I think 30 seconds is up. Rocket Man and Vicky both say Tycho,
Okay.
but since we're looking for a letter, I'm gonna say that Daryl's probably right with Messier and Messier A.
Yes, Daryl is right.
Yay! Congrats!
Yeah. Hey guys, you said Tycho. You know what? Sorry, but it's not uncommon to just not know where you're going on the moon. It's you know, everybody has this. I've had it. We've all had this issue, trying to know what's going on. But those are the craters Messier and Messier A, named after none other than Charles Messier.
Yeah, but I'm guessing he didn't find them. Who was such a fan of Messier that they wanted to honor him.
Yeah, that's correct. They were named. It was named in honor of Charles Messier. Yeah, but that ray structure is really odd because when you see a ray structure like this, it shows you that the meteor that made that hit the moon in a very peculiar way. And I'll tell you what that peculiar way is. It was at a low angle. So when it struck the moon, it tended to throw all of the ejected material downrange from the impact. And that's why we see this like we see it. It's just a very, very cool little crater. Probably one of my favorites, actually.
Interesting.
Yeah, it's really cool. And because we're sort of in a low contrast area, you know, away from the Terminator, we don't get a chance to see the craters. All right.
Well, we actually did have a few questions I was collecting, but Vicky's gonna bust if I don't ask this one. So, sorry guys, I'm gonna ask this one on her behalf first. When you were talking about the moon not having an atmosphere,
yes.
She says NASA said the moon does have an atmosphere, very thin molecules, but it's there. So can we go over it again, please?
Yeah, I've actually talked about that thin atmosphere a number of times, and one of the things that we see is there's a number of sodium ions, then sodium atoms that are surrounding the moon, and here's the thing. Every body of sufficient mass, the moon has somewhat sufficient mass. It's not sufficient enough to carry a giant atmosphere and hold it down with its own gravity, but it can still hold some of the lighter atoms, you know, down at times. And it's holding down some sodium atoms, and I think it might be potassium or phosphorus. I'm not sure, but there is a very, very tenuous atmosphere around the moon, but it's not anything you can even, you know, image. You can't look at the edge of the moon and say, I'm going to take a deep shot and get the atmosphere of the moon. You can't, because it won't work, because it's that thin. You know, it's only a few atoms per, you know, cubic centimeter, you know, so you're not going to see anything. It might even be less than that, actually. So, and the density might be different at different points around the moon as well. The density of that atmosphere could be different. I did see the story. I read it. I studied the layout and the topography, what they thought the atmosphere was, because, you know, I'm into that kind of planetary science anyway, because we have to understand planetary science so that we know what to do when we get off the Earth. But this is, I'm stunned. I got to tell you, man, this is so incredibly detailed and rich. It's just so nice. It's like, wow. You know, I mean, I look at this and say it rivals P&K space imaging And it does tonight. I mean, it really does. You know, Paul and Keith do a fantastic job. You know, those of you that are listening here have also been there, I'm sure. And you're probably also subscribed. Very good. And then you also want to subscribe to Bill New York Skywatcher as well, because he does the wide-angle views. Paul and Keith do views like this. Because it's such a nice night, I thought we should start by looking at the moon a little bit. We'll leave the moon behind in a little while and go elsewhere, because I have several more objects planned for the docket tonight that might be interesting to see. But I did want to just do one more thing here while I have you here.
Well, we have a few more questions on the moon, so
No,
give me a warning before we leave.
I'm not going anywhere. No, go ahead, ask.
Oh, well, this may have been meant for a specific crater we were looking at, but maybe you can... I know there's not really going to be one answer. Ronald wants to know, how tall are these ridges? So what's, I guess, you know, what are the minimum and maximum that we know about so far?
Well, it's true. You're not gonna. We don't have a specific, you know, height, because they're all different.
Okay. Yeah. See, he might have been asking about a specific one we were looking at earlier, but.
Yep. Now.
Sorry, Ronald.
Check this out, guys. In the time we've been talking, okay, there's Okal on the right. Okay. Now let's zoom in again. Remember, when we were zoomed in, we saw the limb of the moon. And we saw Okal. Alright, let's see what we get now. Okay, now if I move to the right here, okay, I go down a little bit, because that's how we were. Okay, now Okal was right there on the right. So how come we don't see it? Where is it? And the answer is that Okal is actually farther away than, you know, it's already out of the region. See that? So Okal is no longer visible in the same view because of this, because of the way it is now. It's already moved out, meaning the moon is already moving eastward in the sky. See? And that's what I think is pretty cool. You know, we look at this and we say, now Okal's here. All right, that's Pi Capricorni. Remember Pi Capricorni, the you know, alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, you know, all the different stellar classifications for the brightness in order in the Greek alphabet. So there's Okal, and now in this short time we've been looking at it. See that? We were looking at it, and it was when I had the moon here. When I first started with Amanda, before we even started off, the Okal was to the left of the word time, and down by about you know, a third of the way. All right. However, in the time we've been talking, Okal has, you know, stayed where it is, obviously, and the moon continued to progress eastward in the sky. All right, as it makes its journey around the Earth. Isn't that great? So you're actually seeing large-scale movements in the sky without even realizing it. All right, so there's Okal is right there at the very edge. Okay, there it is on the right side, and then we just zip over a little bit, and you see the glow of the moon come in. So we're just not quite there. And by the way, just so you know, when we were looking at it, this is the least magnified, obviously. This is the next magnified, but it was actually. I
don't see anything.
Well, there was a star on the right side. The star was there. Okay, now you see the limb of the moon? Mm-hmm. Okay, that's the second level of magnification for this, and then here's the third. Okay, and okay, this is the third. This is what I had when I started the stream. So it's moved even more than you realize, because of the fact that it was used. I was seeing it using different levels of magnification. So Okal has had its encounter with the moon, and now we're done. You know, we're done for another month. But I think Okal will be. I think Okal won't necessarily be, you know, occulted by the moon every night. or every month. That's not how it works. But I just want to point out one global feature here in the moon. When you look down on the moon here, okay, right there in center, if you kind of squint a little bit, you see the dark Maria a little to the right below center, and then another one below that. But to the upper left, there's a crater, a prominent crater in the center. I'm going to zoom in on those. Okay, so right there, you actually see this rim of mountains going into the Terminator, below the screen, and then comes up into the upper right. Then there's a gap, and then it goes and continues up, and then it circles around to the upper left. That is the remnant of a massive impact. Now, that means that something the size of a small asteroid actually struck the moon at one point and created that. That's why the Maria are generally circular. All right, so just an untold amount of violence happened on this moon when it was in its infancy. Now, Amanda, do you have more questions at all?
Yes.
Okay.
Oops. Move that. How much of the moon do we actually see during the month since it rotates slightly? Is it like 67%?
Oh, you mean overall?
Yeah.
It is more than 50%. Yeah, I don't know the exact number, but that has to do with the way the moon is tilted to the plane of its to the plane of Earth's orbit, and it kind of has a slight tilt. And as it moves through that orbit, you actually see this little wobble on a monthly scale. And I don't think it's 67%. That sounds way too high.
Too high, but it's over 50. Do you think by it's just a little bit?
Yeah,
or?
just a very little bit, because you're not seeing. You're not. There's some months when you can see another feature at the extreme edge of the moon that you didn't see the last time, and it has to do with this wobble in the moon's orbit and the moon itself, and it's really cool. And to understand that is just I should actually do a lesson on that for everybody, so we can get an idea of just what's really going on there.
That's a good idea.
Yeah, so I'll do that.
And that last question, that was from Vicky as well.
Okay.
This one is from Laura, who unfortunately had to leave to go to a gig. I hope she enjoys herself, but she's going to listen back
cool.
tomorrow when it's uploaded. So,
all right.
She wants to know, because we were talking about how clear it was and it didn't look wavy or anything, is the clarity due to the waxing moon? Is that why it's so clear, do you think?
No, but
or are we just having a good night?
I think we're just having a good night. It was raining here yesterday. It's cleared out, and then what's left behind usually is sometimes some very still air, and maybe the fronts are stalled or whatever it is, but the air is relatively stable. I knew that it was a stable day when I would see jet contrails that span the entire sky, horizon to horizon. But then, of course, they would just dissipate and go away. When I saw that, I realized that we actually have a fairly stable sky tonight, and that was going to be great. And we do. We have a wonderful stable sky.
So does it matter whether it's waxing or waning that you'd have one image better than the other? Or
no, it doesn't. Okay. No, it doesn't. But that's it's a good point. A good possibility.
Yeah, well, something definitely, if you're going to get into this as even as a hobby, something you definitely want to know.
That's right.
I think.
That's right.
Okay, so I'm not sure what part of the conversation we were talking about, but this question came in from Genghis.
Okay.
If you were free floating in space with no suit, would our heat just bleed out, or would we suffocate first?
Well, obviously we'd be radiating to space, all right? But what would happen first is that your body, which is used to 14.7 pounds per square inch of pressure pressing down on it from all sides here on the Earth, your body would then be subject to a vacuum. And that means that everything in your body would be pushing outward. So, if you really want me to get into the technical details of what would happen, you would basically bloat to death. and
With what?
well, your own internal
What,
pressure.
like, would your organs all expand? Like, it's not
Yes.
like air's getting in.
No, but
Just nothing's holding you together?
that's right. There's no pressure on you. You're used to this atmosphere. Do you realize on every square inch of your body, you have 14.7 pounds pressing down? Every square inch in your body, underneath, on top. It's the weight of the air over your head. It's the weight of the air column. Air has mass, it has weight, and it's pressing down on you. That's why it can be held to a planet by the planet's gravity. It's because it has mass. And so, like, Mars has a minimal mass of an atmosphere. Earth has a substantial mass. The Moon has a tenuous mass of atmosphere. So, Venus has a far larger volume of atmosphere than we do. I mean, Venus has actually got a massive amount, 90 times as much, 90 times denser than ours. So, we've got that. So, if you were just let loose in space, you'd probably, you wouldn't explode, I don't think. But, I don't really want to go into the details. It's pretty gross. But let's put it this way: you'd be dead within seconds. Because
you know what? I don't know. Like, I think in different movies I've seen like all sorts of endings. Like I thought like the half of you that was exposed to the sun would just like instantly fry to nothing, like just charred, and then the part that was away from the sun would just instantly turn to ice. But then, I mean, if there's no air, yeah, suffocation, I would think you'd suffer. Well, I don't know. See, and now you're saying you would, like, bloat to death.
Well, keep in mind, okay, keep in mind that if you look at the nature of your lungs, your lungs, the diaphragm muscle is what pulls in air, okay, and then releases it. People that have problems with the diaphragm muscle, where the diaphragm muscle gets paralyzed, they need to be put in an iron lung to survive. And they were concerned about that with me when it happened to me, when I had that paralysis. But my autonomous, programming, basically, biological programming, still worked, and I didn't have that particular problem, luckily. But if you look at the fact that when you're out in space now you have zero pressure on the other side of your mouth, and you have pressure in your lungs and inside your body. So what happens is that pressure finds an outlet to go out through, and that outlet is your mouth, and so your lungs will be pressed flat, collapsed in an instant. And that flat crushing will just, I can't imagine the pain that would be, but people who've had a collapsed lung, they know what that's like. But you would end up having your lungs just crushed, not by weight, but by vacuum sucking the air out of your lungs.
Okay, well, so you'd be dead from your crushed lungs before.
Yeah, I mean,
your dead body would swell, I guess. And then what?
You'd be swelling immediately. I mean, it would be happening immediately. This all happens at once. You gotta understand. There's no one thing after another. Okay. Now, as far as would you burn up? Well, you would absorb radiation. So the ultraviolet radiation from the sun would be at peak strength and so forth. So you could absorb it, and you're not protected by the Earth's atmosphere. So you would immediately start to, ultravioletly burn. Okay. And so forth. So that would certainly happen. You also would expand, you would bloat, you would also lose all the air in your lungs. So, yeah, I mean, if you really have a really vicious, evil prisoner, if you want to really, torture him and make him go in a very painful way, you stick him in a chamber and evacuate the air, and he'll be gone in a few seconds, but it'll be the most painful few seconds ever, I think, because everything's going to be in play. Everything's going to be hurting. Your blood's going to actually turn to froth. And, when divers get the bends, that's an incredibly painful, that's nitrogen bubbles in the bloodstream. That's from coming up too fast without stopping and decompressing. And if they don't do that, they come up and they get those little nitrogen bubbles, and that can kill them. That's the bends. Well, in a zero pressure situation, your blood will sort of boil inside the veins, and you will get this froth throughout your body, and that'll just be instantly, incredibly painful. And at the same time, the air is getting pulled out of your lungs. At the same time, you're bloating. At the same time, your eyes pop. I mean, it's just disgusting. I mean, there's no coming back from this.
I know you so didn't want to get into it, but I mean...
and I did anyway, and I apologize, chat and folks
Would
listening.
there just be a point where we just, like, disintegrate to the point of, like, atoms or basic elements again?
Perhaps. I mean, if organic matter is consumed by ultraviolet radiation, matter cannot be created nor destroyed. So we're a pile of calcium and potassium atoms and sodium and chlorine atoms, because sodium chloride is Na and Cl, which is sodium and chlorine, so sodium chloride. So all those atoms would eventually be returned to the interstellar medium, yeah. Through some mechanism, and obviously the more radiation hitting the organic matter, the more degradation occurs, and eventually, it's just reduced to nothing again. But nothing like the speed of a phaser from Star Trek, though. That's different. But go ahead.
Sorry, I thought I heard an echo. Daryl wants to know, is it just sci-fi, or could a person really survive a short time in space, as sometimes portrayed as jumping between spacecraft airlocks?
Yeah, like when the astronaut jumped from Hal's or from the pod into the airlock. Okay. I think that's pretty fanciful, because as soon as he opened his eyes, they're going to start bulging, in the zero gravity. However, I think where they get away with it, in that movie is they reasoned somewhat plausibly that the atmosphere inside the pod that got evacuated into that chamber he was going into momentarily increased the pressure in there to some extent. So perhaps that small rarefied atmosphere he could survive in briefly. And maybe that's true. That could possibly be, but you know what? I don't want to test it, thank you. I'm content to stay here and just watch other people do it in movies, okay? But...
Okay, Bobby wants to know,
okay,
did water and amino acids for meteorites start life on Earth? And did all water on Earth come from meteorites? Good questions.
Yeah, actually, that's an interesting question. I'll tell you. This actually is a chapter in my book, and I talk about it, kind of in the, and I joke about it, saying, the history of everything. But yeah, I mean, we look at the moon here, and we see, gray. We see featureless rocks that don't look like they have much in them. They're actually what happens to Earth materials when exposed to the vacuum of space for a long period of time. Okay, the moon is actually very much like the Earth in composition. That's one of the things about the moon that is so interesting, and that is a bother for the lunar hypothesis of formation, which says that a Mars-sized body collided with an early Earth. We don't see any kind of early Mars body stuff, in the Earth, or in the moon, for that matter. So, what could it be? Anyway, so yeah, in the early primordial atmosphere, which there was carbon monoxide, methane, H2O vapor, and some carbon dioxide. The constant as the atmosphere built up, we had lightning storms in our atmosphere, and that was normal. I mean, that was, that didn't take much for that to happen. Static charge would build up between the molecules, and when we started to see clouds, we ended up with thunderstorms. And this lightning constantly striking within this atmosphere had something to do with this. And how does that work? Well, in the 50s, Stanley Miller and Harold Urey created this experiment. Now it's famous. It's called the Miller-Urey experiment. That's Urey, U-R-E-Y. And the Miller-Urey experiment showed that in a flask of primordial atmosphere, as we understand the primordial atmosphere, and in the same flask with a water source like oceans, okay, and in the same flask where you have lightning striking the atmosphere through a spark electrode, okay, this was the setup for their experiment, and the question was, what happens long term? And the answer is, in a week, they discovered that there were like 20 amino acids in this flask that seemed to appear out of nowhere. Now, they didn't. They were synthesized by the primordial atmosphere being struck repeatedly by this spark, which simulated the lightning. So we learned there that the Earth itself made the building blocks of life, okay, the amino acids. Now, further, we have seen meteorites that have fallen here on Earth that delivered amino acid. A famous one is called the Murchison meteorite. You know, Murchison, M-U-R-C-H-I-S-O-N. Look it up. Murchison meteorite. And it delivered amino acids here to the planet. Now, it's, you know, we find one meteor and say, oh, well, you know, a few amino acids, how significant is that? Not very. But when you add up billions of years of meteorite hits bringing amino acids, like the Murchison did, well, then it's very significant. And then we see comets, and comets have water, have hydrocarbon compounds, they have other organic compounds, and they have amino acids. And when comets hit the Earth, they delivered a huge amount of water to this planet in the form of water vapor when they blew up in the atmosphere and so forth. You know, comets very rarely would make it to the planet's surface and go boom and make a giant crater, because comets are actually very fragile. So together, these three techniques created a lot of the amino acids that form the building blocks of life. And because we were in that habitable zone around our star, these amino acids weren't disassociated by a strong ultraviolet radiation. And the other reason they weren't disassociated, meaning ripped apart, you know, molecule by molecule into their constituent atoms, the other reason was because we have a magnetic field. Now that magnetic field is very, very important to us because we enjoy, without having realized it, we enjoy a very nice, you know, relatively calm atmosphere here on this planet. And we do because of the fact that we don't get bombarded with ultraviolet radiation. We don't get, you know, deadly flares that come up and kill people on the sunlight side of the Earth. Okay. Yes, you can get skin cancer, okay, but you know what? Just put put sunblock on, you know. And that's because we have a molten outer core on our planet and a solid inner core. Now, the inner core is probably iron and nickel, and the outer core is made of molten material like that. But when they rub against each other like this, the molten core is moving against the inner core. It's creating a strong current, an electrical current. That current translates to a magnetic field. If you recall in physics, if you ever took physics classes, you learned that if you push current through a wire, it has a magnetic field around it. The magnetic field is induced by the current flow. Well, Earth is just an electrical machine itself, and the dynamo in the middle of the Earth is generating this electric field which protects us from the deadly rays from the sun, the ultraviolet radiation. Why? Because when those highly charged particles and the radiation comes to this planet, it gets stopped by the atmosphere, and these particles, and charged particles, charged energy that's coming to us, actually gets thwarted by the magnetic field and gets caught up in the magnetic field. And they tend to spiral down near the poles, all right, the North and South Pole. And because of that process, we see these beautiful northern lights, we see the beautiful southern lights, you know, the aurora australis down below and the aurora borealis up north. And these are the charged particles entering the Earth's atmosphere and circling around the magnetic polar north and south. Now, that's what keeps us safe. So the amino acids that were formed in this process that I was just talking about with the sun and the lightning and the atmosphere and all of this, and the Miller-Urey experiment proving it all, with the amino acids formed there and the building blocks of life formed like that, they were in a very safe location to develop further. And that's just what happened. You know, the amino acids, ended up becoming a peptide change, and then proteins, and proteins started to replicate. And how did they do that? Well, you know what? We can only speculate through experimentation, but we see sometimes that this replication occurs quite by accident. And even though that's not life, all right, and we'll never be able to say what creates quote-unquote life, all right, we don't really know at this point. I'm sure it's science that we don't know, and it's something we'll maybe eventually know, but maybe we're not meant to know, and that's okay with me, because I don't think we need to answer that question in order to explore the possibilities of other life that has arisen in our universe. And so, but yes, that's how the Earth produced the building blocks of life. And that's actually the premise of my book, The Populated Universe, where I talk about this thing, because this is something that is occurring everywhere we look. Okay? Almost everywhere we look. Okay? Now, on the moon here, you might say, oh, it's just a dead, arid, craters, strewn, dead rock. Well, yes, it's definitely dead. However, it has plenty of water, and water is very important, right? Now, it turns out that most bodies in the solar system have water, and copious amounts of it. Europa, of course, you know about, has plenty of water. Enceladus, which is Saturn's moon, and Europa Jupiter's, Enceladus at Saturn, it's only 300 miles across, but we think it even has smoking hydrothermal vents, black smokers, underneath its surface, indicating maybe it has an underground ocean, like Europa, just smaller. Europa's ocean might be 60 to 90 miles deep, and Enceladus might be a little bit less, maybe 30 to 60 or 30 to 40. But the fact is, this means something to us. This is very important, because this is telling us that our ideas about where life comes from and how life can propagate is something that we've actually kind of got right. We're getting this right. I'm doing a battery change here, so the camera's going to go off for a sec. Ah, darkness. Isn't it nice? So I know it's a long, drawn-out answer, but I think I was on point there answering it. But you'll let me know, I'm sure.
Well, it's a big question. I mean, we like detail.
Yeah, no one. I don't hear anybody arguing and interrupting me, so I guess that's okay.
And see, there was another question that came up, and it got me thinking about a few more questions. So, guys in chat, if you have more questions, start typing them in, because when I start asking my questions, we may go down a rabbit hole. So
you're not gonna get us derailed. Don't worry.
Want to bet?
No, I don't. I have been witness to the derailment.
Well, this question's from Rocket Man.
Okay.
And he wants to know, what diameter telescope would you need to see the atmosphere of a Jovian moon?
You could use a small Sears refractor for that, because all you see is atmosphere of a Jovian moon. You don't see any features, because they are just a giant gas. They're just a gas giant, so you don't see any features like that. So you see what you see when you look at a Jovian moon. What you want to look for are the really tiny delineations between the cloud bands and then the belts. Bands. The cloud bands are one thing. The zones are another on Jupiter and Saturn. They call them zones and bands, and you can look them up. But the difference between them is actually pretty immense. On Jupiter, the zones go one direction, the bands go another. Okay, now how can you possibly have a planetary weather system basically that will drive bands one direction several hundred miles an hour, and then the zone next to it is moving several hundred miles an hour the other way? what would drive that? What kind of system, what kind of internal structure must be in there to be causing this? And that's just one of these mysteries. Now, there's theories, there's wonderful theories actually as to how it all happens. And the other thing is, the white belts of Jupiter tend to be higher in the atmosphere, and then the dark bands are actually lower in the atmosphere. So it's 3D as well. That if you were looking at it from the edge, you would see these large cloud tops, these large white areas, zones, just like elevated in the air, up higher, and the dark ones down below. And when you look at the new imagery from the Juno spacecraft, Juno, look that one up. The Juno spacecraft imagery, you can look for the raw data and see it, and it's absolutely astonishing. You can actually see full three-dimensional clouds rising out of these cloud decks, and then going back down on the other side. It's just beautiful. You can see the three-dimensionality, and sometimes when the sun is just right, you see long shadows on these things. And it's just, oh, you gotta see it. You gotta see it.
Well, see, because I mean, when you were talking about mass and gravity and everything like that, what would happen if, I don't know, I mean, there probably isn't anything that we could think of at this point that would, like, turn the gas giants into solid planets, but, like, if it did, I mean, what would happen? I mean, the sun is still bigger than Jupiter, but would that affect the orbit, having the further ones now become solid?
Well, see,
I don't even know if that makes sense, but do you know what I'm
I know what
trying
you're
to
meaning.
ask?
I know what you're saying.
Okay.
Well, the answer to that question is that, it goes back to what I said before. It's a conservation of mass question. We cannot create mass nor destroy it. Okay, so therefore, if Jupiter just suddenly became solid, it would be doing so with the same mass it has. So it wouldn't gain mass. It wouldn't change its orbit.
I don't understand that.
Well, because
A gas turning into a solid, how can that not change the mass?
well,
I know
because
you said that before, like if our sun turned to a black hole, it wouldn't matter, we just orbit the black hole.
That's
but
right. So that's all the gas plasma in the sun turning to a different type of matter. And the same thing. Now, if Jupiter's 89,000 miles across. So if it turned to a solid, it wouldn't be 89,000 miles across. It'd be far less in size, because all those atoms getting compressed down to a solid would make Jupiter a heck of a lot smaller. Don't you see? So yes, we can, if that happened. Now, but there is no mechanism by which that can happen that we know of. But still, it's a fair point. It's a fair question.
I don't know. I just think of, like, see, and again, I'm not sure where I'm going wrong, but I mean, if you filled up a bottle of water and you put it in the freezer, the bottle could crack because now it's solid, and
oh, but wait.
I mean, it's heavier. it expands.
Is it? Is it heavier?
Well, you know what? I mean, I've never actually weighed them.
Nah, you see, there's an experiment.
But I have. But I mean, with water in plastic bottles, with beer in glass bottles, I mean, I've seen it expand. So, yeah. Because it's changing.
It's changing size because of why? What happens when ice forms? Do you know what's going on? Okay. Why isn't ice...
molecules start moving slower to become more solid?
That's true, but what's happening... That's all true. Very good. Actually, you
That's where my science ended, basically.
Well, actually, you went right to the thing that most people don't even get. Okay, so that was fair. That was good. But I can tell you this. When you look at ice, when you make ice in an ice tray and you pop out an ice cube, is it crystal clear? I mean, the water's crystal clear going in, right? But when it freezes, what happens? Why isn't it crystal clear anymore? It's cloudy, isn't it? It has it's got that hazy white look, doesn't it? Well, what is that? What is that hazy white substance that you're seeing inside an ice cube that was made with totally clear water? It is still your turn. Ding, ding, ding. ding, 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 ding. What is that white substance? What is that white haze that you see in an ice cube? Do you know?
Well, I guess not, because I can't really say ice. It's, I don't know.
Okay.
Is it the salt in the ice? In the
No.
water?
No.
Freezing?
Because
No.
if you're using tap water, you still get it. No,
Oh, yeah.
when you put clear water in an ice tray and then you freeze it, during the crystallization process, what happens is you're getting air trapped in the ice. And so that's why it looks hazy and white and not crystal clear. All right? So, for the same volume of water that you freeze, what has to happen for that same volume of water to freeze but now have an extra volume of air in it as it freezes? For that to happen, you actually have to expand the size of the result. You have to make it larger. You have to have a larger volume that it can fit into, and that's the air that is expanding when ice is being made. So that's why if you freeze an object that has air in it, any object that has air in it. I mean, when you freeze any liquid, you will end up getting a larger volume that's required to hold that. Do you follow?
Kind of.
Kind of.
Kind of.
All right. Well, I mean, I think that's actually a very good question, because it does point out that how people need to think. Because when you look at ice and you look at it, you just observe. You observe the ice and you see that it is no longer the clear water that was filling the tray. As a matter of fact, when you fill an ice tray, don't you always only put in about 3/4 of the amount of water in each little cubicle hole? Because you know it's going to expand, right? And that's what happens when ice freezes. Ice expands, it traps air, and it becomes milky white. That's why ice cubes aren't totally clear. They're not clear.
Because of air.
Yeah, the air trapped in the ice. And that takes more volume. Because you got little tiny bubbles, but you add them all together, and they form the last quarter of the ice tray, when they freeze. I'm going to move us now, but I can come back to the moon.
Well...
Okay, go ahead.
No, again, I don't know. I'm still looking at, like, Jupiter as if when it gets solid, I'm thinking of it like, almost like gas compressing,
okay.
Almost like water turning into ice. And then even if, like, there's air pockets when that all gets compressed, it would still change the mass, wouldn't it? No.
No. See, that's the
Because
thing.
if it's compressing down, a gas giant like Jupiter compressing down to become solid, I can't see expanding like water does to ice.
No, you're not doing the same thing,
But
though. You're not filling your ice cube tray with gas. Okay, you're filling it with with liquid, and then you're freezing it. You're making it go to a different state. Okay. Now, if you heat the ice cube, it turns to water first, and then it turns to gas. And guess what? That takes up even more volume. Okay? That takes up more volume. All right? Because as you heat something, then you have a higher level of entropy, which is, the motion of the molecules are going against each other, and that causes a higher randomness quotient inside the substance, so you end up having these molecules a little farther apart. So the gas actually takes up more space than the liquid, all right? And the solid form of water takes up more space than the liquid, all right? So it goes, the liquid form of water takes up the least, the solid form takes up more, and the gaseous form takes up the most. Now, so if you look at Jupiter, the gaseous form of Jupiter, for this impossible process that could never happen, okay, if we look at this gaseous, we look at gaseous Jupiter, and we think about this, okay, if you compress this gas down, you would find that we don't have any need for that large volume that Jupiter currently occupies. All right, and the reason, of course, is because of the fact that you're taking these atoms and you're compressing them, and when you push them closer together and say form a solid, let's just ignore all the heating and all the things that will happen when that happens. Okay, as you push them together, they're going to take up less volume, because right now they're gaseous, and so the molecules are farther apart from each other. Compress them, they'll be a lot closer together, and make them into a solid, they're still a lot closer together. So that you should see. That shouldn't be too difficult to understand, I don't think. Do you get that?
I get that, but I still don't understand why that wouldn't make it heavier. That's the part I'm not...
Okay, that's I get your issue. Now, the reason that it doesn't get heavier, as I said, is because you're taking the same number of atoms, okay, which have the same mass, and compressing them smaller. That's all you're doing. You're not adding atoms. You're not adding any kind of mass. You're not adding additional atoms. So when you compress them, okay, they just get smaller. They get compressed. All right, they don't get heavier, because being solid or gaseous, all right, you can have the same mass of atoms in a balloon, for instance, all right, and if you compress that on all sides with a higher pressure all around, like say you put it in a pressure chamber, that same balloon that was, say, 6 inches in diameter, full of air, is now compressed down to, say, 4 inches. Have the number of atoms changed inside the balloon? No, right? Because the balloon is containing them. So, is the balloon heavier at that point? It has the same number of atoms, which add up to the same number of masses, because remember, mass comes from adding up the weight of each individual atom in a substance. That's where mass comes from. So when we add up all the mass together of all the atoms, say we have 10 billion atoms, just to say, okay? And say they all weighed a fraction of a gram, which they, nanograms or whatever you want to call it. Let's say you add up the the weights. If you have a balloon that's 6 inches in diameter and you add all the masses together, you get, say, a value of 26, okay, for this 26, whatever the units. Now you compress it, and you compress it down until it's only 4 inches in diameter. You didn't add any atoms to the inside of that balloon. It's still the same balloon. It's smaller. It's closer together. It's more packed. But you still have a weight of 26, because that's the number of atoms that are inside the balloon.
Okay, so... And then what? Okay, we'll keep going with this balloon analogy from 6 inches to 4 inches. Okay, so nothing changes, like the mass of each individual atom or molecule or whatever stays the same.
Yep.
Is there not a point where you compress it so much the atoms like smash together and I don't know, create something else that is now heavier? Like,
well,
no, I get, well,
see, stars do that, don't they? Stars take the lightest element there is, hydrogen gas, which has got a proton and an electron. That's all it's got. Okay? And they take the hydrogen overall, and through a curious little reaction, they do fusion, which creates a helium atom. Well, helium is twice as heavy as hydrogen. So when the helium is created, doesn't that make the star heavier? You may want to ask, right? And the answer is it doesn't. Because to make that helium, 2 hydrogen atoms had to give their lives, so to speak. So it's an even exchange. And that's how this happens. It's an even exchange. There is no additional mass. Now, I know that seems a little odd to you, but I don't want to...
I guess I get it.
I know you don't want to get
because
it,
if you
though,
had
because
like if you had like 10 ones and each of them smashed into another, then you just have like 5 2s. So it's still like...
Yes, it's still 10.
It's still the same, yeah.
See? That's actually a good way to look at it, too.
I like your balloon analogy, because, yeah.
Well, the balloon is a containment structure. It holds whatever's inside, and you can't add any more to it. So you see it. And I've actually done this. I've actually, for one of the TV shows, I actually showed how pressure works, and I actually created a small balloon. It was 1 inch in diameter. I actually can make a 1 inch size balloon out of a regular balloon. And it was a pencil balloon, you know, the ones you make animals with. Well, I know how to make that into one tiny little balloon through a little process. It was something I learned how to do. And I put that in a vacuum chamber, and I did the opposite thing. I took out the air. And what happened? Now, you would say, well, does it get light enough to float? Well, it was just blown up with room air, so it was the same atoms. Okay, it was a mixture. I blew it up, so it had carbon dioxide. It had a little oxygen and a little nitrogen in there. And so when I evacuated the chamber, shouldn't it have gone the opposite way? Shouldn't it have become like helium and start floating in that analogy? And the answer is no, it didn't. It just got bigger. But the atoms were farther apart inside the balloon. Okay? Higher level of entropy in that system. All right? And so there's disorder and chaos. So the bottom line is that this process is actually fundamental to understanding how stars work. Okay? Because, you know, matter cannot be created or destroyed. You can't create mass. You know, mass is basically engineered out of atoms, right? And if you engineer an atom of helium out of 2 hydrogens, you still have the same mass in the system. It's just been redistributed. And that's kind of how this goes.
Okay. Because John has a question. Does a star lose mass in the form of energy? So basically...
Well, the answer is yes. Okay, but that radiative...
But it evens out.
That radiative energy loss is actually something that's been measured in a lot of stars. Some do it more than others, okay, but it's really a fraction of the star's mass over the lifetime of the star, which is interesting, okay. Stars lose most of their mass when they die, okay, because they lose their outer layers, like the Dumbbell Nebula that we know and love so well, and the Ring Nebula, which we of course also know and love so well, and that's what happens, you know. But over the course of their lifetime, they lose a fraction of their actual mass, and that's what happens. Now, you may wonder what this is on the screen here. This is actually the primary star in Capricorn, which is Alpha 1 and Alpha 2 Capricorni. And that's a star called Algidi, and it's a cool name. Algidi, hey, how you doing? You know, but you can see the star with your eye, but it's actually a double star, and you see it here. And it's actually a very interesting star. It's 4th magnitude, basically. And you can see the stars are separated by what that distance you're seeing there actually is 53.2 arc seconds. Okay, that's the distance that you see. All right, so you can get an idea of how big my field is here by seeing this. And then it's actually 570 light years away. Okay, so that makes the separation of these stars in real units that we know just over 9,000 astronomical units. All right, so that's actually quite distant. All right, it's really cool. So now the thing is, they both shine this yellow-orange color, and I can do our little trick here. We can do the stellar defocusing just to show you that. Another thing you can do if you don't want to defocus is you can tap the mount. Okay, and if the star is really bright, you know, have a bright color to them, you'll see it there. You know, you'll catch it in your eye. In this particular case, we can't see it, so I'm now going to defocus these and show you how that looks.
Yeah, and the red you're seeing, that's just pixelation,
That's right.
right?
That's actually
Yeah.
from the camera sensor.
Hmm.
Now, keep in mind that we're sort of canceling out the red color because of the fact that we actually have a special filter in here that is preventing us from seeing this just like you would expect. So what I want to do is do one thing. I'm going to actually take that filter off. Is that okay with y'all? And we'll come back in just a second. I'll do it right here while we're staying live. I won't even go to commercial. Just kidding. I don't do that. All right, so here we go. Let me. Sorry, you got blared. Okay, so what I'm gonna do is open this thing up. Come over here. I'm gonna turn the camera off just for a minute, because otherwise.
It's a nice Halloween orange.
Yeah, it's orange, and for people looking at this in the dark room, they're going, "What the?" And they're gonna be just like blown out. So I'm gonna, and I'm also putting on my red light. So I'm just taking this filter off for now, so we can get back to what we know is more realistic colors. Okay.
Okay.
Okie dokie. Oh, you know what I just realized?
What?
I don't think I need to do this. Actually, I don't need to take it all apart and take it out. I actually just take this off and put on a different adapter, which I have for just this sort of occasion. And where are we? Okay, where'd you go? Where is it? Is this it? Hey, here we go. Look at that. Okay, and now I'll put us back on the straight and narrow here. Okay, this is a adapter-free, that is to say, filter-free rather, view that we're going to be seeing now. I'll have to refocus, but I was out of focus intentionally anyway, so we're okay. All right, let's get the camera angled right. All right, so I took it off, put us back on, attach my cable back to the main telescope again. Here we go. All right.
So now with this one, we're gonna see
Colors.
what it actually looks like the truest kind of image.
Yeah, and now you can actually see it.
Yeah.
Right there. All right, so let's go zoom in. We are, of course, there. Okay. Now we're seeing these in their true colors. Okay. And let me just focus a little. Let me bring the focus down manually here, just because I don't want to get us in trouble with the focuser. Trying to do it here. Come on. Here we go. Okay, so now I can focus. Alright, so there's what they look like, okay? Now if I go out of focus with them, alright, now you can see, now we're really close to the moon right now, but you can see that they're glowing orange. They have an orange glow. Do you see that?
I do.
Yeah.
It looks like all the colors are kind of going around in a circle, but yeah, mainly
yeah, the predominant color. Yeah, because you know what you're getting, okay, is these stars are actually fairly low to the horizon. The moon, they're lower to the western horizon than the moon, and when we look at this, we actually see the scintillation in the nighttime sky, the atmospheric scintillation it's called, and that actually causes them to look a little strange, right? But if we take it out a little bit more, okay, and let's go down, bring them down a little bit, center them up. See that? So now we got them there, and you can see they're predominantly the orange color. All right, and now we'll come back to focus. Okay, so we're actually seeing a fairly good representation there. Now, what I want to do though is, just for fun, let's actually let's go back to say 250 ISO, and let's go up to 1/8 of a second, and let's just see what we get when we look at them now.
I said dome.
Yep, you did. Alright, let's take a look at this.
It must be an alien dome on one of those stars.
Yes, that's right. It was an alien dome. So let's go to our image and let's go zoom in a bit. Let's see what we get. Are we going to see anything? Oh, darn it all, hold on. Alright, that wasn't what I wanted to do. Okay, I want that. Then come back. That's what I wanted to do. There's our stars, and now we zoom. Yeah, see there's actually a little little tail there because I forgot to come back down and make the have a timer to go 2 seconds before it actually takes the picture. Now it's doing that, and now we'll get a clean shot. Okay, so let's go here, let's go here. Now we can zoom in. Alright, now you can see now they have a little more of an orange color. Alright, but let's just do a, let's do 1 point, well no, I'm going to go up in ASA too. Let's go up to 800 ISO and 1.6 seconds. Here we go, and done. Now let's see what we get. I don't want to wash out the color, I just want to make it just right so we can see it. Now you also notice that there's also another companion by the other star. But you can see these are actually kind of an orangey stars, and they're really, really pretty stars. And that's Alpha 1 and Alpha 2 Capricorni. Okay.
Capricorni.
Algidi. Yep. And it's actually...
So is one hold on. Is one Capricorni and one Algidi?
No, they're both... These two stars make up Alpha Capricornus. Okay? But the stars are called, if you want to look at them as separate, they're Algidi Prima and Algidi Secunda. Okay, so Algidi Prime and Algidi
Prime, yeah.
in second, yeah. Pretty cool. Very, very nice. Really, really nice. I like those.
That's funny. Did an Italian find these, or like
You know,
usually it's like Alpha? Why are we going Prima?
yeah.
Don't hear that often in space. Well, I haven't. Is that a common thing? Is it? I thought Alpha would probably be.
Well, Alpha means the brightest, you know, and it is Alpha Capricorni and Alpha 2 Capricorni. Alpha 1 and Alpha 2. And they make up the main star because they're a double star. All right. And
Ted wants to know which is which. Which is Prime?
Segunda, Prima's on the right and Secunda's on the left. Just so you know.
Okay.
Now, the interesting thing is these stars are actually G3 and G8 stars, by the way. Okay, and Prima, the one on the right, is a G3, and the one on the left is Alpha 2 there. That's actually a G8. No, yeah, G8. Let me just move these up so you can see them better. Isn't that cool? I mean, that's really neat. But Alpha 2, that is the giant star that we're talking about. That's actually a giant that's 43 times more luminous than our sun, and it has to be fairly big. And then the slightly farther star from us, Alpha 1 Capricorni, is a supergiant, and that's 930 times as luminous as our sun. And it's actually 21 times more luminous than the other alpha star that you see in the same image here. It's really kind of cool.
I see a question. I'm not exactly sure. I think there may have been a fun little autocorrect.
Okay.
Cuppy wants to know, I heard that stars can be so bright that other stars are dimmer. Get outshone? I'm guessing maybe get outshone? Maybe?
Get outshone?
The other stars look dimmer? I don't know. I heard that stars can be so bright that the other stars are dimmer. I'm not sure what the end means, but she wants to know if that's true or not.
Well, yeah, I mean, if you have a bright star, let's go actually to a binary star system where one star is a normal dwarf star like our sun, and the other is a supergiant. The supergiant will look massively brighter than the other one, but the most of the light that would be hitting your planet in your binary system would be coming from that supergiant. However, take the smaller dwarf out of that system and put it on its own, and it could illuminate the Earth and the whole solar system just fine. And it will have a brightness all its own. It'll still be, very, very bright. But compared to the supergiant, it'd be that much brighter. It's really, it's a matter of degree and it's a matter of comparison, and that's what this is all about. Okay, so that makes sense. That's a good question, actually.
Yeah, I just wanted to make sure that I asked it properly. She rephrased it, and that's kind of how I was reading it.
Yep.
Stars next to each other that can be kind of outshine the other ones. Yeah.
Now I'm going to go just a little above the moon, and let's see if we can. Let's see if we can see something else that I was looking for here. Oops, that goes up. Okay. Alright. Down in the lower right, we have our target. And I'll bring it around and bring it up. Boom. Okay, so it's right there now in the middle. Right in the middle there. What do you suppose that is?
It's a pretty color.
It is, isn't it? I'm going to zoom in just so you can see a little better. Okay. Let me just drop a little. A little more. Okay. Let's do a image here. Let's go. Let's say ISO 1000 for 1 second. We'll start there. With the moon, we got to be careful. We don't have a filter on here, so okay. We're gonna go a little more, maybe, but I'm gonna just check first to see if this gives us what we want. Okay. All right, there. It's right there in the middle. Needs to be a little, probably better focused. So what I'm going to do actually is, let me do a focus shot here, okay?
Okay.
I want to just do that first. So let's go up. All right, and this is live 4K view. Let's go over to one of these stars. We'll go here. Alright, let's zoom in, start zooming.
Why are we going in on any old star?
Oh, we're only going in because I really want to focus the telescope a little better.
Focus on the blue one.
Well, because the thing, that's not a star, actually.
No, I know.
Okay.
I said blue one.
Okay.
Not blue star.
Okay. All right.
I don't think it's a star.
It's not. I know what you might think it is. You might be wrong.
Oh, I think it's her partner. I think it's a little too dark blue. I could be wrong still. I probably am, but...
Yeah, I don't... It's,
Is it a planet?
Oh, you're trying to spoil the fun already? Come on. Don't be spoiling the fun. Okay, so here we go. Now...
No, well, while you're focusing, people in chat can be,
guessing.
Yeah.
Okay, there we go.
Because when we first got here, I thought it was actually a little darker blue than I'm used to seeing.
Mm-hmm.
But now it's actually starting to look...
But you're looking at it in a 4K view, that's why. And when you're seeing it in a 4K view, the color does appear to be a little enhanced. Okay, but I want you to look at the shape of this. Okay, I want you to notice the shape. I'm going to come off of 4K, and I'm just going to do. Well, let me see if I can do this here.
Am I going to see it on Skype though, or should I flip over to YouTube?
No, you'll see it on Skype. You're going to see it all on Skype. You're not going to have any problem seeing it on Skype.
No, I mean the setting. Is it going to change in Skype? I don't think so.
No. Okay, just a sec. Let me just do. Let me get rid of the high ASA. Let's go down to, say, 500 and 3.2 seconds. Let's see what we get. Remember, no filters now. We're just looking at the raw colors. All right. Now you say, well, wait, that's kind of dim. Yes, it is. There's a reason why I'm showing it to you dim.
See, now it looks a darker blue again.
Yep. But if you look at this very carefully, you'll see that it's not looking like a round planet, is it? It doesn't have that look. It has something a little more oblong. So this is something different, not a planet. Okay.
Uh-oh, I led Chad astray.
Yes, you did. But it's okay.
It's not a planet, and it's not a star?
No. 6 seconds at ASA or ISA.
I thought you were giving me 6 seconds to guess what it was. I was like, oh my god.
No, I'm just going to do a 6-second exposure. And in that time, if you're not done, you're done. I'm just kidding. All right. Let's zoom in.
Okay, come on, guys, help me think. It's not a star and it's not a planet, so what else could it be? Well, I'm guessing it's not a moon.
No.
Unless it's actually a blue moon, and
oh,
be awesome.
Once in a blue moon, yeah.
Oh.
If you look at this, you're going to see some structure in it when you look up close. It has some interesting structure.
Is it a nebula?
It is indeed a nebula.
Is it a nebula we've seen before?
It is a nebula we've seen before. However, we haven't ever seen it without the filter. Now we're seeing it without the filter.
Should there usually be a red ring?
No, no. This isn't the red. This isn't the, no.
Okay.
Oh yeah, I'll just tell you. This is the Saturn Nebula.
I was just about to say that because you were talking about the ring, and I was thinking, how cool is it that it was named the Saturn Nebula because it has a bit of a ring.
That's right.
And yes, I do see the. I don't know. I mean, it's hard to really say it looks like a ring, but it almost looks like there is like a wisp in the middle.
That's correct. There is. There absolutely is. Oh, you know what we're going to do right now? While I've got this here, while I've got us looking at an unfiltered view, let's see if I can see it. Ah, we can. Okay. I'm taking us over to one more object before it disappears for good. And alright, I want to show this before it disappears for good. There it is. Oh, everybody's favorite double star. Okay, this double star we're looking at right here is one we've seen before, but we have been seeing it. I tell you, to be fair, we've been seeing it under magnification and filtering, and I meant to say filtering. So when we're looking at this, we're trying to figure out what this is, what the colors are. It's actually kind of important not to use a filter when you're trying to actually discover what the colors are. So this is my favorite double star, and I wonder if the folks in the chat know what my favorite double star is. I'm going to give you a little look here of it. We're going to zoom in a little more. Okay. Okay. There you go. And I'm going to focus now.
There you go. This is Mark's favorite double star. What is it?
Okay. And now if you look at the colors, all right, very orange and very blue.
And remember the little mnemonic device, O be a fine guy, kiss me, or O be a fine girl, kiss me.
Yeah, like OBAFGKM.
Yeah, but random letters that don't spell anything are meaningless. You gotta tell them the little thing.
No,
So whatever
it
your preference
spells-
is, just change the G to a girl or a guy. But it's O, be a fine girl or guy, kiss me. And that's how you remember. It's the luminosity scale for stars.
Almost. It's the spectral scale, the spectral class. Spectral class.
And the O's are the hottest and brightest.
That's correct.
And biggest?
Typically, yes.
Typically, okay.
And then
And then as you go down the scale,
Yeah.
they get more blue.
Well, actually, no. They get more
No.
red.
They get more red.
You're doing so well. That's okay. You're fine. Yeah. and
Well,
so-
because I'm thinking, I need simple analogies to remember, and I like the lighter analogy that if you light a lighter, the really, really, really hot part of the flame is blue,
That's right.
and the cooler is orange. I don't know why I said it backwards then.
I don't know, but that's okay. You got it now. So now these stars are literally 430 light years away, but at that distance they're separated by 34.7 arc seconds, which we talked about in fractions of a degree. There's 60 minutes per degree, and there's 60 seconds per minute in degrees. So these are separated by a fraction of a minute, that is half a minute basically, 34.7 arc seconds. And at that separation, at 430 light years away, they are separated by just over 4,600 astronomical units. So it's pretty impressive. Impressive, most impressive, but you are not a Jedi yet. My favorite line from Star Wars. Okay, anyway. So
Joseph's guess is Albireo, but I don't think that's a double star, is it?
Oh yeah, Albireo is definitely a double star, and the blue one is actually a B8, okay, and the orangey one is actually a K3, but the K3 is a giant, all right, but the B8, the blue one, is actually a regular main sequence star. So it's smaller, but it's brighter than the K star, but the K star is larger in size, so it has an overall apparent brightness to us that's brighter. So that's why they look relatively equal in brightness here, which is kind of interesting. Okay, the surface of the K3 star is only about 4,400 degrees Kelvin, and that Kelvin scale, but the surface on that B star is quite a bit hotter, at something like 11,000 degrees Kelvin. So we're looking at the difference basically in size that's causing them to appear, equally bright. Okay, on its own, the B8 star would actually be very, very bright, and closer to us it would be like one of the Pleiades stars. So, and speaking of the Pleiades, even though the moon's out, we'll try taking an image of the nebulae around the Pleiades to see if we can actually see the blue without the benefit of a filter. We might, maybe we won't, but we'll try it at some point. I'm really hoping that we'll see. I'm really hoping we'll see the Orion Nebula before I have to go in. Okay. All right. Well. Okay. This is.
Wait.
Yeah.
Got some more guesses?
Okay.
Guess some more guesses before you say. John says something Cygni.
Yes.
Oh.
But not.
Okay. Good. No.
meaning that it's in Cygnus. Yes.
Okay, because Kev says Miser and Alcor.
Very good guess, because those are doubles, but no. Miser and Alcor's on the other side of the sky, and the Big Dipper, and that's actually we can't see it from here because it's behind the trees. For now, it'll be up again.
Okay.
Another 12 hours, it'll be up again.
I think that was it. And the only one I can think of, for some reason, I don't think this is right because I thought the one on the left would be at the bottom and the one on the right would be like at the top. For the one I'm gonna guess.
Okay.
You want my guess?
Yeah, but keep in mind you can't go by that because at the angle that the telescope is pointing at, that could actually make this that's called the position angle, the angle of the blue one relative to the orange one, appear differently. So, it's not necessarily the case that the angle is important. But go ahead, I want to know your guess.
Okay, well, because it's the only one I can think of.
Okay.
Epsilon Lyra?
Oh, no, but that's actually a good guess. It's nearby, but it's actually, Epsilon Lyra is a little too, it's smaller in actual size, so you can't really see it too well. On a night like tonight where Lyra is almost behind the house in the distance here. But
this is in Cygnus.
This is in Cygnus now.
And okay, so this is just a double star. This isn't like an asterism. This isn't like a.
This is a true double star. These stars are 4,600 astronomical units from each other, almost 4,700 AU, separated by 34, by half an arc minute from each other.
I hope these numbers are clues to people in chat, because.
Well, I mean, the color is the most important thing here. We've talked about this B8 K3 double many times, and we've seen it.
Is it something alpha and beta?
No.
Or one of them beta?
No. Oh wait, I mean, there's another clue I can give you that might be interesting. You like these are our little trivia quizzes. You like these, guys? If you do, I'll do more of them. If not, I'll just dispense with them. But I just thought this one was kind of fun.
I think people like games.
Well, yeah, maybe you do. I just hopefully.
Well, I mean, their answers are coming up.
That's good.
Mm-hmm.
So anyway, this does have another name. Okay, it is actually. I wonder if this will give it away. Well, you know what? I'm gonna move on anyway to another one. But this is Beta Cygni. It's the second brightest star in Cygnus. So now you should know what this is.
Well, no, I don't. But yeah, I just asked if it was Beta something. So kinda. So what is it? Beta Cygnus?
Yes, Beta Cygni. Yeah.
Beta Cygni.
Yep.
Because I saw Albireo come up, but that's the brightest star.
No, it's not.
No?
The brightest star in Cygnus is a star called Deneb. Oh.
Is this Albireo?
This is Albireo. Yes, it is. Okay.
Oh, okay. That might have come up earlier then.
It did, and I was about to say it, but you said, no. All right, whatever. No. I didn't want to bother with it.
Oh, no. No, I think you were going to give the answer before I read the answers in chat. Maybe that's why I said no, don't give it away yet.
No worries. You're not gonna. I'm not gonna give it away. So let's see. So
I can't find who said it, but congratulations. I did see it come up in chat. So whoever said it, good job.
Yeah, I know. That was nice.
Mm-hmm.
All right. So now I'm gonna lower the dew cap because I'm gonna move around another fairly. Oh, look at that. Remember what I told you about?
So why is this your favorite?
Look at it. It's beautiful.
Oh, I know, but
that's why it's my favorite.
Just because you find it aesthetically pleasing? It wasn't the first double star you saw, or
it was one of the first
the biggest double star.
It was one of the first ones I ever saw, and as a kid. And that's memorable. What can I say? It's really pretty. It's really pretty, really pretty. I'm gonna take us to one more place now because I think the zenith is good for this. But the moon is out, but we'll try it anyway. It might just be a little brighter. Okay, and we're going now. We're moving. Okay. bottom, but it's just a little fuzzy. We can't really tell right what it is right now. I'll have to move it up into the view shortly. But before I do that, now I extend the dew cap. There we go. Well, that keeps the dew off our lens. That is our corrector plate. And now let's bring it up. And there won't be any equivocation because you'll all know what this is. Even though we're taking a photo of it in this moonlight, it's actually gonna look really interesting. Actually, probably I think with this, we'll see. We'll find out. So let's 12,800 for. Let's just do it 20 seconds at 12,800 for now. Might be a little bright sky. Might get pretty bright. Sorry, I have a cough. I apologize for that. I'm not sick. I just, as I've told you before, I have one paralyzed vocal cord. That's one of the remnants of the stupid thing that happened to me a couple years ago. And
the cold makes it tense up more, doesn't it?
Yeah, it does. It makes it kind of hard, but it makes it rather rigid. So as long as I talk and keep it warmed up, you see, it's gonna be fine. Okay, so this guy you're about to see here, it's 20-second processing. There we go. Whoa, it would have helped if I focused, don't you think? Now we were focused before, but you see, sometimes what happens is when you move the telescope, it can get out of focus, and that's kind of a sad but true thing that happens. Is all instruments have that problem sometimes. So let's okay, let me just hold on a second. What's going on there? All right. All right, wait a minute. Okay. Just a minute. Let's see what we got here. Okay. Okay, what's going on here? Okay. My camera's actually doing bad things. I don't like what it's doing, so I gotta figure out what's going on here. One second, folks. I'm just trying to figure out what's going on with the camera. Just a sec. Okay, so it was that connector. Okay, good. I know what I was doing, I think. No, I don't. Okay, hold on. Getting a camera error here. The camera's taking on a mind of its own, doing some stupid things, so I'm trying to...
Didn't you do that once? Didn't you, like, burn something out? You used it so much? I don't know if it was a telescope or a camera or...
Oh yeah, I was using one of my cameras so many times that actually I took a picture and the camera just went boom and it just exploded. Because the very powerful spring-loaded shutter inside the camera decided to crap out really, really bad. Crap, what's going on here? Why is this doing this? Might be related to something else. Hang on. Turning off the camera for a second. Sorry, folks. Sorry about the delay. I'll try and get us back on track here in just a second.
Well, that's the thing. I just don't want to... I don't want dead air, but I don't want to distract you when you're working on fixing equipment.
No, it's fine. You can talk. I don't have any problem with that. I'm I'm trying to figure out why the camera's doing what it's doing.
There were some little things I pulled up before the show.
Yeah.
Things coming up in the next month or two, Space Watch wise. So
yeah. There were actually.
Let's see if there's anything else.
Yeah, I think talking about I think when you were talking about some of those things that were coming up, we had. Let me just try focusing this right now. By the way.
I don't know if you guys knew, tomorrow, October 28th, is International Observe the Moon Night. That's really cool, eh?
I know, that'd be
Institutions
cool.
worldwide will discuss the importance of the moon in everything from eclipses to tides to astronomical observations.
Sure, that sounds like fun.
Well, we're going to have a Rocket 9 launch on the 30th of October.
That's right, and then we have Orbital ATK sending up a rocket.
That is on Halloween. That's on the 31st, yeah. They are going to launch 6 SkySat Earth observation satellites for Google and Skybox imaging. Very cool.
Yes, indeed. In fact, that's I'm partial to Orbital ATK because I know the CEO, David Thompson.
Cool.
And David called me one night, or I called him actually, I can't remember who, when he was about to launch from Wallops Island, Virginia. They were about to launch a bunch of satellites from their rocket that they built down there. And he was nervous and was hoping it would go off without a hitch, which it did. To their credit, they know how to do things. There's no question about it. They know how to do the work. So they did a really nice job. Okay, 25 seconds at 10,000. I believe I've got the camera functioning again. But we'll see in just a minute. Well, in 25 seconds. And I focused. And then we're going to take the camera over to the Pleiades after as well. So overall, how are the volumes between Amanda and myself? Are we doing okay now with volume?
Let us know, please, chat.
Because in my ear, she's just fine. But in your ear is what matters.
Mm-hmm. Yeah, I mean, that's the thing. Like, I had my computer, like, the volume on the computer turned down. I had the volume in Skype turned down. I tried to move my microphone away from my mouth.
Yeah.
But I get excited. I'm a very loud person. I don't mean to be.
Look at this, folks. This is the Andromeda galaxy.
Oh, much better.
Is that not beautiful? Wow. I mean, this is one where we actually. Okay, it's not. It's doing this crap again here. I don't know why it's doing this to me. Let's go over. Oh, come on. What's going on here? I do not want my camera suffering failures like this.
Everyone's saying that the sound is good. The music just started blaring in my ear. But
it's not
still the echo.
But it's not blaring in their ear. That's the thing.
Yeah, well, as long as it's not, yeah. I know the other night, Keith and Rocket were on, and you went to get a battery or something.
Yes.
You left us alone, and the music came on, and it was just blaring.
Oh, really?
Yeah. Like, we couldn't even hear each other on Skype, so just listen to the music and look to the picture.
Wow.
But no, they all seem to think the volume is sorted now, just the echo. And I don't know what's causing that, so. Thank you for your feedback, everybody.
What's going on here?
And I've never played Portal, but I think Steve Merchant actually did a voice in that game, Portal.
I don't know who he is.
Stephen Merchant is Ricky Gervais's writing partner.
Writing partner, okay. Writing partner, not writing partner.
Rating. No, they're all straight.
Oh man, what's going on here? That's the, wait, I go this way, and it doesn't crap out.
Star party, is it?
Yeah, that was a star party. Then when I come back this way and I go to an image, I just leave it. I just let it sit there for a second. I want to, like, see what happens. I've got plenty of battery. Okay, and if I see what's going on. Okay, 1 second, folks. I gotta take the camera out again. I see what's happening. I have a loose contact here. Okay.
Yeah, as long as it's just a connection problem and nothing when you change filters, that nothing.
No, it's not that at all, actually. Alright, let me just... Okay, so let me just do this. Reseat these things. Man, that's just not... I don't like this. I actually changed the adapter. I did. I changed the adapter around a little bit. Okay. I'm going to have to refocus again. Let's see what we got here. Camera goes on. You don't want your camera that, you know, you spent thousands of dollars on, you know, just kind of crapping out, you know.
Yeah.
Okay, that seems like it's working right now, and we still are a little out of focus. So let me go into 4K mode here again, and let me see if I can do this. And I'll focus now on some more stars that I can see. Okay, I'm just going to focus a little more here.
Well, I mean, it's a beautiful image, so it's definitely worth the wait.
Yeah, I hope so. Okay, I just focused again. I'm cutting the recording. And now I'm going to do 30 seconds at, I want 12,200 or so. 12,800. 12,800. Yeah, 16,000. Okay. 30 seconds, here we go. Did it do it?
And before I give any false information in chat, we are looking right now at the Andromeda galaxy, are we not?
Yes.
Okay.
Okay, let me just make sure. Oh, we got that going. I gotta change that.
Dana, that's a hard one to wrap your head around. I mean...
What's that?
I don't know.
Here we go. 30
We're
seconds.
just a tiny little dot in the Milky Way galaxy, and yet we can see another galaxy from your front yard. I mean, it's
within
so
our own.
weird.
Well, you know, I mean, it's actually a marvel to think about how this.
It's stupefying. It's incredible.
Well, there are some strange differences, you know, that when we look at, you know, a galaxy far away. You know, we also think about the fact that this galaxy far away has its own stars, has its own stellar nurseries, has its own hydrogen alpha regions, you know, and things like that, and it looks beautiful, you know. And that's what we see when we look at other galaxies. We see them sometimes better than we see our own, because from within our own, we can't see through our galactic disk to the other side. We've never seen it. We've never seen it. We've only inferred it. We've only gathered what it might look like. Yes, that's a little high, but you know what? It should work. Look at that. That is just really pretty. In spite of, you know, you can see these dark lanes in the galaxy very well. And the focus is still not quite perfect. Oh man. Yet then you look at a bright star there in the center and it looks kind of sort of like it is. Well, I'm near the edge of the field too. Being near the edge of the field causes problems. Boy, that's pretty. So if we look at this again, let me now do this. I'm going to go to 4K mode for a minute so I can see the galactic center. There it is. Now let's move.
And tell us again what's going to happen when we collide. Are we just going to pass through and be a little bit different on the other side, or are we just going to merge into a big super galaxy, or
Well, that's the thing.
what's the most likely scenario?
Well, we're certainly going to merge to some extent. We're going to merge in some way. We don't know how, but we're going to merge. We're going to merge with this galaxy that is. I'm going to go down to 12,800, by the way, for 30 seconds. We're gonna merge, all right, but we don't know what it's going to look like on the other side. There's a theory that says that when two galaxies collide that are spiral galaxies, we're a barred spiral galaxy, which means that we have spiral arms, but through the center of our galaxy we have a fairly heavy concentration of stars that form sort of like a straight bar through the middle of our galaxy, and the spiral arms seem to emanate from those. If you look up barred spiral, B-A-R-R-E-D, spiral galaxy, then you'll see what we think we live in. All right, sort of a barred spiral. It could be a hybrid too. It doesn't have to be one or the other. It could be sort of a hybrid. But we're a fairly big galaxy. You know, we're good size. You know, we're over 100,000 light years across, and it's a big galaxy. So that said, I think that given that we are such a beautiful call them island universe of stars, we actually have our own we have our own dark nebulae, which you see here. These are these dark lines, these dark strands, the tendrils of black that you see. Those are dark dust and molecular clouds, okay, and those are molecular clouds that actually make up the disk of a galaxy, and it's in those dark clouds where stars and planets are born. There's gas in there, there's dust in there. Like we see with the Pleiades was formed in a bright knot of hydrogen gas at one point. However, when they were born, they blew away all the hydrogen gas, and they're hot. And if there was gas around them, we would still see we'd see a nebula around them that's emitting that characteristic red light. But we do not. We only see blue, and that's because of the fact that the Pleiades were so strong and energetic that they blew the gas away, because the gas is very light and could be the atoms of the gas could be pushed away with stellar wind. Now it could be that early on the Pleiades did have a reddish nebula around them, and it faded over time, leaving just the blue behind. What's the blue? Well, the blue is where the light from the stars simply is reflecting off of the dust grains in the dusty nebula that's left around the stars. See, stars form in dust and gas, and gas or gas and dust. And when they formed, the gas got blown away, and the dust is heavier, so it didn't get pushed away by the strong stellar winds. All right, not as fast, not as rapidly. So we see that going on in the Pleiades. We see that going on, in other galaxies. Even when we look at other galaxies, I'm gonna try.
Well, yeah, because that was John's question. Hopefully that answered it. I'm not sure. He said, when I'm looking at Andromeda, it's like a mist. So each particle in that mist is a star. You're saying that the dark parts have stars?
No, I'm saying the dark parts are areas in the galaxy where there's concentrations of dust and mixed in with the gas. And that dust is something that comes from all the many supernovae, and then it gets gravitationally attracted into the galaxy and starts spinning around the disk in the same way. I mean, seeing a lot of gas and dark dust like this is typical. We see this in the Albireo galaxy that we've seen before. We've seen it in the Black Eye galaxy that we saw way in the beginning of SkyTour LiveStream, which we'll see again. And we've seen it in other views that we've had. So it's really something, you know, to see this dust like this. And we're seeing it from afar now, and kind of on an oblique angle, kind of looking down sort of on the top of the galaxy, or the bottom. There's no up or down in space. So, you know, it looks kind of cool. I'm going to take us to another place now. I know this is beautiful, but I want to go to another object to see if we can see something in particular that I want to show you. So I'm going to go there now. And again, as the moon is lower on the horizon, we don't have to worry so much. Let me go and in 4K mode and see if we can see what I'm looking for.
And there were a few other questions that I'm kind of falling behind in, sorry guys.
That's okay. I think I see what I'm looking for. It's down below here. I'll find it. Let me see if I can bring it up here. Okay, I'm moving up a little. Yeah, there it is. Okay. Okay. Now I imaged this the other night and I have yet to upload it, and it came out gorgeous when I imaged it with the filter. So now I'm going to image it now without the filter, and we're going to just take a look at it and see how it looks. In a dark sky site, I would never have to do this. I would never have to use a filter. I would just not use a filter that I would use to like filter out any glowing, you know, sky glow. That is pollution, you know, because I wouldn't need it. Okay, the thing I'm imaging now is called the Mesher 33 in Triangulum, the triangle. Mesher 33 is actually a spiral galaxy. It's actually a fairly loose spiral galaxy. There's different levels of spiral. You can have a very tight spiral, which is an SA, okay, or an S0, SA, then SB for looser. That's kind of like us, and then SC for really loose. And these really loose galaxies, man, you gotta watch out for them, man. I'll tell you. So this is
a new insult.
Huh? Oh yeah, well it could be a new USC, huh? What? Oh, why'd you call? Oh, okay, just a little.
Ooh, oh, hold on, let me warn the chat.
Yeah. Oh, my mistake. I actually forgot to turn this back down to a reasonable ISO. My apologies.
I can deal with the orange. It's the bright white light that I tried to warn people
Tell them the
about.
supernova's coming. Yeah, I'm doing it again. I apologize for that. It's just so much fun to be able to just drive the telescope to these objects. But you know what? I worked for this. I worked for this effort. You know, I worked to make it happen. So, and I make no mistake that it can go haywire. Like tonight, the camera was misbehaving. I don't know why. I think that it has to do with the way the adapter is seated on the camera itself. So I'll have to be aware of that. Okay, so now we're going.
And if you turn on the light in the dome to look around and see what you're doing, that's going to mess up the focus of the telescope.
Not the focus. It'll mess up the image that we're taking, because stray light will potentially get into the telescope.
No, well, if you're not taking a picture at the moment.
Well, light won't.
If you just turn on the light to see what's going on,
yeah,
and then turn the light back out and take a picture, won't. Like with a normal camera, you know, you have to give it a second to adjust to different lightings. Would that not interfere? Do you know what I mean? Like, would you not have to refocus?
No, focus wouldn't matter. Yeah. No. This is the galaxy. Look at this. Isn't this beautiful? You can actually see the spiral shape. Now, it's a face-on galaxy to us. It's looking right at us, basically, face-on. So you can see the spiral arms way out there. Do you see that? But there's something cool I want you to see. Okay, let's look over here. Right there. Kind of right near the center. There's that kind of little, outside the major central area there, and outside the arm. You see this sort of isolated little poof. See that? Okay, and let's zoom back out. And let's look at another one. Okay, if we come over here. Okay. And we look here. You see that one? That's another one. You see that right there?
That's really pretty.
Yeah. What that is, that right there, okay, that is a giant star-forming region, a giant stellar nursery, as seen in another galaxy, okay? And this galaxy, the Triangulum galaxy, is a little bit more distant than the Andromeda galaxy. This is 2.8 million light years away. The Andromeda galaxy is 2 million light years away. And that star-forming region is actually basically a red H2 region. And the color would show up if we process this well. And and this galaxy has a lot of star-forming regions. It's knotty. It looks really knotty. K-N-O-T-T-Y. Okay, knotty. Not naughty. Right. But you also see, for instance, little ones like right there in the middle. Okay, that one there. Okay, is there. There's a number of them in this galaxy that are just
go back up to that one. It looked kind of like purplish and yeah.
Yeah, that's probably a region that's you can kind of see there's a little red color in it. It's very faint, but you can see it. But this might be an OB association. That is an O and B star association.
An O and B star association.
And B. Yeah, OB. They're called OB associations. I'm not sure if this is an
like
OB.
find.
Yes, exactly. That's where it comes from.
Yeah,
it's an OB association. Young stars and spectral class O and B, potentially. And if so, it's a very hot blue area, which could also explain why we don't see a lot of red around it generally. But it is.
Well, hold on. An OB association.
Yeah.
Are there only 2 stars there?
No.
An association be a whole bunch of O's and B's?
Yes, it can.
Would this count as a cluster?
Yeah, it would be a cluster as seen in a distant galaxy. Yes.
Wow.
Now look at, you can see the dark lanes. That is the dark molecular clouds in the center of this galaxy as well. See those? I mean, that's just amazing. I love that. And this is actually, sorry to come down here, but this is at 12,800 ISO. If I go to 16,000 and do 30 seconds, it's probably going to be a little too bright. But I'll try it. Let's just go up another stop just to see if we can pull out a little more detail. I mean, without a filter on here, you're getting more than natural color at the expense of the extra glow that's coming from the night sky. Now here's something interesting that you may not know. Even in the darkest places on Earth, if you take a view of the night sky, you're going to end up with a potential green glow in your images. Alright, and you say, well, why is that? Does anybody know?
Alright, chat, you guys are up. Why do you see a potential green glow? And I don't know. I should know because you've told me enough times. It's very rare to see green stars. It's usually blue or red, and green's not a very common color.
Yeah, but that doesn't have to do with anything here, unfortunately. That's just it just has the word green in it. But that's the only similarity. Okay, but that's okay. I mean, that's a good thing to point out because then I could say that has nothing to do with it. Okay, let's see if this works. Now see how this image is bright. This image is bright, of course, because of the fact that we're taking such a longer exposure, but with a deeper view by this. I'm gonna process this singular image later and see what I can get from it. But you can see, hey, look at that. That's a beautiful area right there in the galaxy, right there. Actually, right there in the middle. That's pretty. You can see the spiral shape very, very clearly. And you know what? I gotta tell you this. I've never seen the Triangulum galaxy. I've never seen it until I saw it in this dome. So it was the other time we saw it, the last time we saw it, the other day. That was the very first time I've ever really seen it in my life. I've never seen it before except in pictures.
That's so crazy.
I know. You would think.
I mean, you lived at observatories. I mean,
Yeah.
you've had access to how many countless telescopes and
Yeah,
so many different locations. Like, I don't.
Well, I mean,
I mean, yes, the universe is big. There's a lot to look at, but I mean, things like this.
But why does this
Well, I
happen?
mean,
See, why is that? Why do we?
now can you even prioritize? You know, these are the top 5 things I want to look at first
Well, actually,
from everything in the world. You know.
well, what happens is that when you're working in an observatory, you're working on a research program, and every second you're at the telescope is money being spent. You know, part of the endowment, part of the program monies, and so you don't want to be sitting there joyriding around the universe. You actually got to do the work. So I never even thought about taking this to, like, you know, look at Jupiter or do other things. You know, taking the telescope there. But I actually did one night take the telescope that I was working on and move it over to Jupiter. And I had to catch my breath, because I could easily see, without even trying, I could count 19 cloud bands on Jupiter so easily, and I could see sharp little distinctions in them and things flowing around. It was just so beautiful. Absolutely beautiful.
Well, I think we have the answer to, does chat like playing trivia games? Because we have a ton of answers on why. Let me get back to the top here. Okay. Cuppy says atmosphere. Vicky says green is the color of the chemical makeup of the star. Ben says some kind of copper oxide reaction. Ted says blue from the sky, yellow from the sun makes green. Love that answer. Joseph says space clouds. Vicky elaborates on atmosphere around the star. Mineral content around the star. Ozone. John says ozone.
Okay, and
green star answer, red star by another is an illusion. Okay.
Well, actually, my point was, when you take an image of the night sky, say even on wide angle, okay, we're not looking at a particular object up close. Even in the darkest place on Earth, and especially in the darkest place on Earth, okay, then you could actually see a green haze in your images, especially if you're aiming toward the horizon. You might actually see a greenish haze on the horizon, and you wonder what that is, okay, and that's something called sky glow. And what is sky glow? Well, our atmosphere is made up of nitrogen primarily, and a smaller amount of oxygen. But what happens is, during the day, the nitrogen molecules are absorbing radiation from the sun, and at night, oh wow, sorry, I'm on the Pleiades right now, and at night what happens is you can actually see at night that the nitrogen molecules will actually emit the stored radiation that they've had during the day, if you want to look at it that way, and it comes out in a green glow. So our atmosphere glows green, and that's a very real effect, a very real thing. Now here in the Pleiades, you can see now, you can see the blue reflection nebula here. It's very clear actually. When I'm using the blue filter, it actually is a little harder to see actually, which is unfortunate, but that's okay. So now when we look at this star, you can actually,
that's beautiful.
Yeah, this is that little arc of dust being illuminated by that star. It's a very dusty region. Okay, very, very, very neat area. When we do some piggyback stuff a little later on in the winter, we're going to actually image the Pleiades, and the Pleiades kind of fits right in the view, and then when we image them deeply with the filter, you're going to see all the nebula, and it's going to look just astonishing. It'll be really, really pretty. So So we're looking we're looking at Merope. Alcyone is at the bottom. Merope is over to the right. I know the stars are kind of all the same brightness. And let's go to Maya and Electra. Let's go up. We're gonna go up a little. Yeah, go up there. Go the right way this time. We're gonna go this way. All right, now we'll image this end of the Pleiades and see what we get. All right, let's do this with the 30 seconds at 12,800 and see what we get. Again, I will process these one-time shots, one-shots anyway, and then give them to you so you can see. All the imagery is made available on the SkyTour LiveStream companion site on Facebook, which you can go to and check out the gallery of images there. And don't forget, you know, if you want something in particular, if you want a raw file that is a absolutely raw file right out of the camera, all you have to do is just, you know, let me know. You can tell me, ask me for it on the site, or you can send me an email or talk to me through the SkyTour LiveStream site, and you'll get it. Now my email, you can get my Gmail. It's on the SkyTour LiveStream channel site. Is mufonanalyst@gmail.com. But you know, you can actually get to me pretty easily that way. And if you haven't subscribed, consider subscribing, because I'd love to, you know, build up my base of people that I take with me everywhere in the world that I go. And I would love to be able to share my experiences with you. You know, not that I'm anybody special, but you know, it is kind of fun to do it in a group. You know, you can clearly see the blue in here. You can see the blue mixed with the darker areas. And when I process this later and get a little more contrast in here, then you'll actually see the division between these colors very clearly a little later. But so that's beautiful. The Pleiades has shown up nice tonight. It's actually a relatively, you know, clear night, even with the moon out. So that bright area, that bright sky you're seeing, that's actually moonlight. That's just bleeding over right now. So yeah, that's sad but true. You know, the moon is still giving us some trouble here.
And just so you know, Vicky actually very sweetly tweeted out links to your 3D printouts that you're doing. So thank you very much, Vicky.
Thank you, Vicky. That was very kind. Very, very kind. Thank you.
And I think it was her earlier in the chat. Someone said that they were looking at all your stuff and they definitely want one. They just have not decided which one. So
well, they can tell us which one they want, and we'll print it for them if we don't have it out or if we haven't done it already. I keep printing these out, you know, because I just, you know, I'm printing actually Herschel crater right now in the shop. Herschel crater's sitting there going zzz, 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 you know.
Okay, we'll kind of explain for maybe some newcomers. You can get like an actual blueprint of kind of any image on the moon, several planets, several of the planets' moons.
Well, yeah.
And you actually recreate three-dimensional printouts of, you know, a crater or a.
That's right. That's right. We can actually. I'm sorry, I was moving to an object, so I didn't. I'm moving to another cluster here. Yeah, this this whole thing we're doing with these craters, it started quite by accident. We weren't planning on, you know, producing printed craters. It just turned out that we discovered that people wanted them and people thought they were really cool. And you know, I have access to the data. I mean, I have Pluto, I have Mercury, I have Mars. Well, Mercury's partial. I have Mars, I have the Earth itself, I have the Moon, I have Ceres and Vesta, you know, the asteroids. Well, so Vesta's an asteroid, Ceres is a dwarf planet, right? And so it's actually interesting that the whole approach actually kind of sort of took on a life of its own. And
yeah, those are just the ones that he's printed so far. If there's something he doesn't have, I mean, if the blueprints are there, it's just a matter of printing and making it, you know. So
yeah, I actually have the whole moon.
it's really great.
I talked to the USGS guys because I'm helping them with their troubleshoot the system at times. And I asked about the remaining data on the moon that isn't available anywhere, and they said, oh well, here. Wow. And they sent me this beautiful links to these they're not online, but these offline this offline imagery that was just it's not imagery, it's actually they're called digital elevation models. And so when the space probe goes to these planets, okay, like Mars, okay, the Mars, the MOC, Mars Orbiter Camera, goes around Mars, and it takes these laser altimetry readings on all the heights of all these objects that it's bouncing a laser off of, and then based on the reflection of the light coming back, it can discern the heights of the objects it's passing over. So little by little, it builds a height map of all of Mars, and so the height map of all of Mars exists. And then there's and then there is when the Dawn probe went to Vesta, the asteroid Vesta, and then the dwarf planet Ceres out in the asteroid belt, same thing. It measured the altitudes of the planet, of the dwarf planet and the asteroid, and that data is available. And so I take that data and I got to bring it into another program to create these height maps properly, and then from those I create a file that can then be 3D printed. It's a fairly lengthy process. It takes time to do, but I got it down to a science. I went onto the moon thing just before I came out here. I grabbed Herschel Crater from the online data repository, brought it down, made it into a printable file, and I printed it all within a matter of about 10 minutes. Right? The longest time I had to wait was the time it took for the online server to do my batch job, which is a job that's done without me touching it, and produce the file for me, which it did. And I grabbed it and I was emailed the links to it. I downloaded it, and then I converted it over, brought it into the program that I needed to convert it to the proper grow object, and boom, off it went. So that's how fast it is, and that's what we would do for any of you who want to get one of these. Now you're probably thinking, well, what's the price? And that's a good question. I'm trying to work out what the price is going to be, because I want the price to be something reachable, and I want it to be something that isn't going to be at all beyond anyone's means. It should not be beyond anyone's means. So we'll make sure that it's something that anyone can afford. And
Chad, what do you guys think? For those of you that have actually seen his work before, just I think fair. Chad is quite fair and honest.
Yeah, I'm very much a big fan of their thoughts. Obviously, I wouldn't be doing this for them if I, and we're not going to get rich off of this. We're not looking to. It's just something we can do. It's something we can offer, and so we want to.
Definitely.
That's it. That's the whole point. The whole point of what we do.
And it's something so unique too. It's not like all your friends are going to have one. You know what I mean? Like,
yeah, I mean, I wouldn't let all your friends
have
have
it. An astronomer lover in your family, Maybe very.
Yeah.
He's present. Vicky wants to know. I think you were talking about yourself, but she said last night when you were on Bill's, you were talking about someone going to the Ozarks. Yeah, I'm assuming that was you in April.
Yeah, I'm going to be.
What's the Ozarks and why are you going?
The Ozarks is it's a 30-year running UFO conference, and they've actually extended an invitation to me to come talk this year for the first time. I've never been down there. It's in Arkansas, which I think should be pronounced Arkansas. Okay, there's no W in that word. And if it was Arkansas, that's how you'd say it, because you like saw. But the bottom line is that the thing I do when I go to these conferences is I try to be the voice of reason, right? Just like with NASA's Unexplained Files or What on Earth. I mean, I get these show stories, and they say, what do you think this is? We think it's this, and I say, actually, that's not that, but I can actually reproduce it for you, and I can show you how that can happen. Okay, and then we do that, and so they're used to coming to me, give me a story, and what they say is this. Okay, they say, and they're British, so they come in and say, Mark, okay, we'd like you to build up the story just a little bit. Say, this is something very interesting, or something like that. Your own words.
Where are these people from?
Britain, Great Britain, London.
Ew.
And they say, and we'd like you to be able to just tell us it's interesting, and then you can destroy it after. And that's they're used to telling me now that I can destroy things after, and it's like, but I'm not here to destroy things. I'm looking for truly anomalous things too. So it's not like I'm trying to destroy your ideas. It's just that if they aren't correct, if there's another explanation, then I just want the opportunity to be able to say what this could be. It could be something else. It could be this, that kind of thing. So that's something that I've had to deal with. And it's fun. It's a lot of fun talking to these guys. And they're a lot of fun too. Let me see if I can. Oh yeah, that was too much.
And
yes.
Cuppy was mentioning something about a yellow star we were looking at. I don't know. She just said yellow star.
Yeah,
is there a yellow star you can talk about there?
Well, that was if it was a while back, that might have been Alpha 1 and 2 Capricornus. Remember?
I think it was in the whatever we were just looking at.
In the double cluster. Yeah, there is actually a really pretty red star in here. And let's just go there now.
When we were talking about the double star, however, Ronald wanted to know how they could be different if they were in the same system. Like how could one be, what was it, M and K? No.
B, A, and K.
B and K.
Well, it depends what their starting conditions were. If one star had the lion's share of the hydrogen gas, then it's going to potentially form a hotter star, and thus last longer on the main sequence, burning and fusing hydrogen into helium ultimately. But in the case of the K3 star, it was already a giant, and the reason it was a giant is because it's already used up its hydrogen. So stars are different. Stars act differently throughout their existence, and so they may very well excuse me they may very well utilize hydrogen in a faster rate, for instance, and that's something that we could have seen here. That's what could have happened in this particular case. And I'm doing a 10-second exposure, by the way, at 10,000 ISO, sensitivity. So the stars could, once they form and they become main sequence dwarfs, fusing hydrogen into helium, then what they do, that's the double cluster, by the way. It looks beautiful. Then what
that is apparently the one at the bottom is the yellow star Cuppy was referring to.
Oh, really?
Yeah.
Let's see which one she's talking about.
I see a few that kind of look yellow.
Yeah, I mean,
I see 3 on the left and one kind of in the center and one at the bottom.
That's the one I thought she was talking about. I'm assuming Cuppy is a she, by the way.
Cupcake Christina, I think.
Oh, Christina. Okay, yeah.
Christina, yeah. Like Cuppy Cake, don't you love that? It's hilarious.
Yeah, I think it's great. Great name.
It's hilarious.
I mean, I would have called myself Cupcake LiveStream if I, had the, thought of it first. I'm just kidding, Cupcake. I wouldn't take that away from you. So anyway, you can see this orange star, this yellow star, which is there. It's a beautiful field star in the double cluster region. Look at that, huh? And then the double cluster itself have, between them, there's some stars that are just on their way toward evolving off the main sequence, or potentially moving off the main sequence. But no, I'm telling you, it's beautiful, and so that's what double cluster looks like, kind of to your eye when you look up in the sky. And then
would we see this just with our naked eye? Really?
Yeah, I can see it right now. And I look out, I can see the double cluster. You kind of have to know where to look, and you have to use something called averted vision. What that means is you don't look directly at it, because the cones, the color receptors in your eyes, are not as sensitive at night as the rods, which are the black and white receptors. The rods are around the outside edge of your eye, so when you're staring straight at an object at night, you're not seeing it as bright as you could. So when you look at a faint nebula in the sky with your eye, you look right at it, and then you kind of look away from it, just like avert the vision, kind of just go off to the side, so you're seeing it through the edge of your eye. And all of a sudden you see so much more detail. It's really pretty, really pretty. But actually, so in a reasonable dark sky, this is how you might see the double cluster. Okay, let me just show here. So you might see it like this to your eye, but in a dark, really, really dark sky, you might see it looking a lot brighter, kind of like this. See how that looks? That's more pretty, isn't it? And we're looking at it, of course, in 4K mode. That's why you're seeing it here. We're in 4K live video. So we shut that off, and then we just get down to plain old, this is more limiting. That's sort of a native, ability for the camera. So now, I think one of the other things, the last thing I can look at tonight is, again, we're going to do this without a filter, so it's going to be a little bit bright, guys. Actually, I don't know. No. Let's see what we're going to do here. This is my Navajo song here.
I know.
It's just like it's a rhythmic drum beating thing. It's a very nice meditation type song. Just like bum 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 bum. It's like cool. Okay. All right, let's go to that. Okay, we're gonna try and go and see if we can look at this. But before I do that, let me just see the outside of the dome.
But before that, something totally different.
Yeah, right. And now for something completely different. Know what that's from?
Monty Python?
Oh, yes.
Sorry, I hope that wasn't rude chatting.
No, it's alright. I thought it was funny.
I was just hoping you weren't going to get a copyright burn.
No, not at all. Not at all.
We do still have a few more questions coming in.
Sure. Go ahead.
Vicky wants to know, so when we say star, do we mean suns?
Absolutely correct. But just to dispel one little myth right there, we don't. When we say star, we do mean suns, but in the broadest sense of the word. We don't mean just like the sun, because there are stars that are so big that if you put them in our solar system, they would actually go out all the way to the orbit of the planet Jupiter. Okay, there's one particular star, I think it's VY Scuti, S-C-U-T-I Scutum. Yeah, S-C-U.
Scutum?
Yeah, Scutum. S-C-U-T-U-M is the name of the the constellation. it's so big that you would actually end up with a tremendous, you'd end up with a tremendously, our solar system would be nothing like it is now. Uranus and Neptune would be boiled away, okay, at their distance. It's just incredible. 10 seconds at 10,000 in the sky glow, no filter. Let's see what we get here for the Orion Nebula, Messier 42. Just
What would happen to Pluto with Scutum?
What do you mean?
Well, if you said Uranus and Neptune would be fried.
Oh, okay. Well, I think the ices on Pluto's surface, which are mostly nitrogen, would actually be be very much sublimated. Okay, we're gonna do this.
Would it just boil away though? I mean,
that's what I mean. It would be.
Oh.
It would sublimate. Pluto has an atmosphere, but you know what? The atmosphere is mostly nitrogen because it has nitrogen ices on its surface. So it's kind of interesting.
Well, if nitrogen heats up, wouldn't it explode?
No.
No.
No, not at all. Nitrogen, it's nitrogen gas, when in the atmosphere, and it's liquid nitrogen when it's a liquid, and it's nitrogen ice when it's solid. Okay. As you can tell, this is the Orion Nebula. Like I said, I just want to zoom in and see just how bad the sky looks here. Check this out. Okay, when we look in the center of the nebula, okay, you see all the dancing around we're seeing there? Just imagine when we're taking a picture, the telescope's almost horizontal on the horizon. Those four stars are called the trapezium, and those are the stars that are actually powering this nebula. I said this before. And they're actually born in this nebula. They're illuminating the nebula. And perhaps, like the Pleiades, they may eventually disperse the nebula with their solar winds, their stellar winds. And so when we look at this, they're called a trapezium, of course, because of the nature of their shape. They look like a little bit of a trapezium, a trapezoidal shape. Now you'll see that the colors are dancing, and nowhere is that more evident except when we actually defocus. Watch this. Look at that. Okay, now watch this. Watch how this looks. I mean, it might as well be flashing lights, right? See, this is our atmosphere. This is what happens, folks. It really ruins our views, and this is why we're looking through more what's called air mass. We're looking through more air when we're looking horizontally like this, because remember, the stars are a long, long way away, okay? And the atmosphere is curved around the Earth, and we're looking through a long stretch of it before we get out into space and onto the clarity of the stars beyond. So we don't see these in the clearest way right now. When it's overhead, it'd be so much more clear. So when I try to take a picture, for instance, like I did there, I'll take a, let me just say, I'll do 15 seconds at 2500. So we're going to go 5 more seconds. And all that dancing around is going to affect our image. And it's going to really kind of make our image look a little bit out of focus, when in fact it's not. But the air dancing around ruins all the subtle details. That's why you need to look at objects when they're near the zenith, up over your head. That's the best time to see objects. Okay. That's why the Andromeda galaxy looked gorgeous before, because it was right over my head, right overhead. So there we go. So now you can see.
That's gorgeous.
You can see the nebula here, but you also see it, and it's actually kind of blurred out. It's not as sharp and clear at all. Okay, and it's beautiful, yes, but unfortunately, it's not as good because it's really again, the telescope's almost horizontal. In a couple more months, we'll be out here doing this again, but we're going to be doing this using using a little different approach. We're going to make sure that we take the approach of looking at objects near the zenith quite a bit, because that's going to be most important for us to do. Now, let me just, I'm really cold right now, and I'm probably going to have to end, but don't Don't run away yet. I do have something else I want to show you.
Okay, well, we still have a few more questions, so while you're moving.
Yeah, go right ahead. I'm gonna, okay, I'm actually gonna move to this guy right here. One more thing here. Moving. Okay, this is a little higher in the sky than the last time we looked at it. So this might be okay. Let me go into 4K acquisition mode just to see what I got. Boom, boom, bum, 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 bum. I love that thing. Okay, if I move it up, is it going to be down there? Let's see. There it is. On the next clear night, I have to spend time realigning, because in the cold, everything gets chilly and bolts loosen up. And I've got hundreds of pounds of telescopes sitting on this steel pier. And as you move the telescope around over time in the cold, with that movement, the pier begins to, the pier will begin to, you know, migrate a little. So you have two choices. You can either work on the telescope up above, or you can cinch up down at the bottom with the pier and get that to work better. So we'll do both. Okay, so let's go back to 20,000 for no, let's do 12,800 for 15 seconds. Let's see what we get here.
Okay. Vicky wants to know, in the Orion Nebula, where the trapezium is found.
Yes.
Or sorry, where the trapezium is. She's saying they found more water than there is in the whole solar system. There. Is that true? I'm not sure where she read that, but...
Well, the thing is that these... Oh, there we go. Hold on. These locations in the that region, actually, we find that these... That's the Crab Nebula, by the way. We find that these objects will have a varied spectrum, and that's what she's responding to. And that maybe that's true. I don't know about that research. I didn't read that paper at this point. I mean, I will, and I would like to understand it and get another understanding of it, but I haven't read the paper, so I don't know. But if she says that that's what she's read, I'm sure that's true. They might have found some water out there. I'm going to shut the camera off for 1 second. And I'm going to take this out. And man, every little knobs on telescopes really are very, very difficult to move when it's cold. Okay, so let's put this in here. Get this on here with our wonderful filter, and now we will compare.
Oh yes, and there was a question from Cuppy a while back.
Okay.
I actually missed that one. I apologize because it was a good one, because I remember hearing something like this. When you're talking about water on the moon and such,
Yeah.
is that water drinkable?
Well, I mean, you have to condense it, but there's no reason it's not. You know, I mean, if it's water with other compounds in it, then no, you want to be careful, right? But most likely it's it'll be water that's isolated in a crater, so it'll just be regular ice, and that might be just fine. Don't know, you know. I'm gonna.
I don't know if it was Tim Peake or the other Tim.
Okay.
But one of them, when they were doing a spacewalk, moisture started building up in their helmet
Well,
and
yeah,
they
'cause-
told like I don't know, ground control or whatever you call them, and they're like, yeah, there's moisture building up in my space helmet outside of the ISS, and they're like, oh, stick your tongue out, taste it. And he did. I mean, never in a million years. I mean, your tongue could burn off. I mean, that could be acid. You don't know what that is. I mean,
well, if it's inside a space helmet, you do. It's actually the condensation from his breath. That's what that is.
I think it was. I think it was a leak in a tank or something.
Okay.
Because I think they said, does it taste salty? Because then it would just be your own sweat or something, or something from yourself. But I mean, still, I don't know. That's would you? I think I've asked you this before. Would you taste the water? Would you lick the inside of your space helmet?
Yeah, I mean,
That's crazy.
I don't think you could actually reach the inside of your space helmet too easily, but yeah, why not? Okay, there's the star I gotta focus on right there, guys. So I'm gonna try and focus with this first. Hold on a second.
Okay.
Okay, good.
Slam Dunks wanted to know. He said, I assume he, sorry. They said, I can't see the color difference in stars when I'm looking through a telescope, but I can see it here. Why? Because he doesn't. They don't have a filter.
Yeah, I'm actually. It's because I'm actually. I'm defocusing the images. You know. So when I defocus the images, your eye can see more. Surface area that it couldn't see before. Follow what I'm saying? There's more surface area.
No, I don't think it's. I don't think they were talking about the defocusing. I think like when we were looking at the the B and the K.
Yes.
Like I think maybe with their telescope they're just seeing maybe just white stars. Maybe it's not as close up and they're not seeing the color. I'm not sure why one telescope would pick up color and another wouldn't, unless it's just not powerful enough to get as close up to see the color. Is what I'm thinking.
It's not a matter of close up. I think having a volume of light come through does help with the color a little bit. Because now, when you have a volume of light that's coming through, that's more light that can hit your eye and more chance of kicking off those cones, the color receptors in your eye.
So it could be light pollution.
Yeah. Well, actually,
or maybe even a full moon. Because wouldn't that wash out?
Yeah, a full moon will, and light pollution will wash out. Yeah. So, okay, this is the ring nebula. This is the M1 Crab Nebula, and this is the Crab Nebula without the filter. Can you see the difference? Okay, there's the Crab Nebula with no filter, and there it is with a filter.
That's what I'm wondering. If he doesn't have a filter, that's why it looks black and white.
No, it's not that. It's just that a larger light bucket like this can actually deliver more color to your eye. All right, and you need certain thresholds met. But you saw in the double cluster, and that in a small telescope, you can see that orange star in between the two. Look at that. That's pretty, huh? You can see the filamentary structure in there. This is one of these objects that you have to stack. And do stacking with to actually, see what's really going on in it,
I didn't see an orange star in it.
Huh?
Did you say you could see an orange star in it?
No, in the double cluster.
Oh. I was looking, I'm like...
No, in the double cluster. They're double cluster. Yeah, in the double cluster. Well, anyway...
There's one more question from Ronald.
Sure.
What's the temperature difference between the light and the dark?
What's that mean, light and the dark? I don't know. Light and dark what?
Light and dark. I don't know. I was thinking the color difference myself when I first tried it. Sorry, I'm going back and forth here.
No, it's okay. I just don't know what you
What
mean
is the
by
temperature difference?
temperature
Light and dark.
difference.
Maybe when we were looking at the moon? Maybe on either side of the Terminator?
Oh. Well, it depends on where you are in the moon. It depends on how, what the sun's doing, how it's striking the moon, what angle of incidence, you know. But a direct sunlight coming straight down on the moon will, you know, heat up the lunar soil underneath to some extent. You could actually, you know, see it glow in the infrared, because infrared radiation is just light. Okay, so that makes sense. So the glow would be from heat rising off the moon. That is the infrared radiation. So that you could see, and the temperature would probably be several hundred degrees in the lunar regolith. If you could take a temperature inside the regolith, which is lunar soil, and then the temperature in the dark areas right next door, there'll be a tiny bit of conduction of the heat through the soil, but not much. And it depends how it's packed. If it's loosely packed, then you won't get much. If it's tightly packed, then you will get more. If it's solid rock, you'll get the most. So if that conduction, if the sun heats that up, then we can actually, you know, see that potential thing happen. We actually see that where there's differences in temperature sometimes, these can be responsible for moonquakes, because like a lava tube might heat up from on top. The top surface of the lava tube may heat up, and it's all vacuum inside the lava tube. There's no air in there or anything, but the lava tube, which is basically rock, is heated up to the point where it gets hot, and then maybe it cracks. And when it cracks, it makes these little moonquakes, you know, and it can crack across, you know, maybe 100 miles worth of lava tube, and so you can get moonquakes, and we still detect quakes on the moon from the detectors and seismometers left by the Apollo astronauts. So, you know, we noticed that, you know, that kind of stuff still happens. Anyway.
Okay, well, that's it for questions.
Oh, good, because that's it for me. I'm really cold. So, guys, I want to thank you for coming up tonight and spending this evening with me. And I will be back again. Let me see if I can get back to. Yeah, we can leave you on the Orion Nebula. We'll be back to this again, and you know, later on in the season, we'll do a spectrometer looking at the Orion Nebula. We'll see the Orion Nebula in its emission colors, which is really cool, as well. Now that's a little more involved, and it's going to take, you know, it's an effort to get it all hooked up. But once it's all hooked up, we go for it. We just check it out and look at it. It'll be a kind of a different night, but it'll be fun. So.
It's always fun seeing these things and learning these things, and
yeah, you know,
throwing out random questions and seeing where it takes us.
Yeah. Well, here's what's nice about it. Even though sometimes we look at the same objects, we have different conversations, don't we? We talk about different aspects and different things, and I think that's pretty cool. And that's what I'm all about. I'm all about, you know, mixing it up and changing, you know, our view of things. And we were going to get to the upcoming launches and missions, and we talked a little bit about them. You did, anyway. But we didn't even go beyond that because we got too caught up in other things. So it's like we never have time to get through the things we want to get through, folks. But I tell you this, I'd rather use up my time not getting to everything we want to talk about with you than anybody else. Okay, because you guys are great. You are just helpful. You're smart. And, you know, you're an intelligent group, man. And I just want to thank you for joining me. And if you haven't subscribed, you know, please do me the honor of subscribing. I would love to, you know, have you join my my SkyTour LiveStream family here and just have a lot of fun, because I really am having fun with you guys, and I really do enjoy doing this.
And make sure you hit the bell. It's right beside the subscribe button underneath the picture you're watching. Because that way, next time he goes live, you'll get a notification so you can come and watch us live. And if there is anything you want to see or ask, you know,
that's right.
You have the opportunity, so
right.
take it. I do.
Yeah.
And I will, so trust me, get your questions in. You don't want to hear some of the stuff I come up with, so.
Oh, nonsense. She does great. I want to thank you all. I want to thank Paul and Keith for P&K Space Imaging and Bill New York Skywatcher for getting me into this whole thing and getting me to do these streams from the very beginning. I want to thank you, Amanda, for joining me. I want to thank all my mods in chat, and I want to thank everybody that has joined us and watched us, and especially the subscribers. If you're interested in anything that we're doing as effects models, if you want to talk about lunar craters, Martian craters, Ceres, Vesta, Mercury, Pluto, any of that stuff, let me know, and I'll be happy to talk to you about it. Other than that, I had a great time with you guys. I can't feel my feet, and you know what? It's worth it because I've got you. Thank you so much, and I will see you next time, and keep looking up.